Hello there, and welcome to Physics with William, where curiosity settles in softly and even the smallest ingredients of the universe are allowed to take their time. Tonight, our attention turns toward a particle that sounds almost polite when you first hear its name, as if it might be something neat and self-contained, something that would sit quietly in a tidy row of scientific labels and behave itself. But the Lambda particle is not especially tidy, and it is certainly not well behaved for very long. It appears, it exists for a fleeting moment, and then it changes. That brief little life, almost too short to imagine in ordinary human terms, tells us a surprising amount about what matter is doing beneath the surface of everything we can touch, hold, build, or break. It is one of those lovely scientific cases where the name feels much calmer than the reality. A Lambda particle sounds almost decorative, like a symbol that might live quietly in a notebook margin. In practice, it belongs to the lively, crowded, slightly unruly world of particle physics, where the universe reveals that what looks stable and solid from a distance is often built from things that are anything but. The chair beneath you, the walls around you, the air between one thought and the next, all of it comes from a hidden layer of restless ingredients that do not experience stillness in quite the way we do. And somewhere in that hidden layer sits the Lambda, one of nature's more intriguing short-term arrangements, a particle that manages to be both ordinary enough to study and strange enough to make generations of physicists stop, stare, and ask what exactly they were looking at. Before we wander any further into that small and rather unstable corner of reality, I would love to know where in the world you're listening from tonight, and what sort of hour it is in your little part of the day. Are you hearing this late at night with the lights low and the rest of the house finally quiet? Are you listening under a blanket with a clock glowing gently across the room? Or perhaps it is afternoon where you are, and the universe of subatomic particles is simply your chosen companion, while the kettle cools and the world does whatever it insists on doing. There is something fitting about asking where you are while beginning a story about particles, because location matters more than one might think. At the human scale, it tells us whether we are tucked into bed or halfway through a long commute. At the particle scale, it tells us what fields are present, what energies are available, what interactions may happen next, and whether a tiny piece of matter will remain as it is or almost immediately become something else. And if you find these quieter journeys through physics soothing, interesting, or just a good way to let the mind settle, while it still has something worthwhile to chew on, I would be very grateful if you gave the video a like and perhaps subscribed as well. It helps this calm little corner reach other people who might enjoy a gentler way of meeting science. I do always hope these topics are relaxing enough to help you drift, though I must admit particle physics does occasionally have the opposite effect. It has a habit of making the universe seem both more complicated and more intimate at the same time, which is not always the ideal recipe for immediate sleep. Still, if you do remain awake for a while, at least you will be awake in excellent company, with quarks, decays, and fleeting particles passing quietly through the night. Now, the Lambda particle is not usually the first guest invited into a popular conversation about physics. When people think of tiny things, they often begin with atoms, and that makes sense. Atoms feel manageable. We were all introduced to them early, usually with diagrams that show little electrons sweeping around a nucleus in a way that is not quite right, but is friendly enough for a first meeting. If curiosity survives that first introduction, one might later encounter protons and neutrons, those occupants of the atomic nucleus that seem sturdier and more serious, like the reliable furniture of matter. And if curiosity survives a little longer, then eventually someone mentions quarks, and at that point things begin to feel less like furniture and more like a locked backstage door has been opened by mistake. The Lambda lives behind that door. It belongs to the family of particles called baryons, which means it is built from 3 quarks, just as the proton and neutron are. So in one sense, the Lambda is not some wild outsider. It is a relative. It belongs to the same broad household. It is assembled according to many of the same deep rules. It participates in the same basic architecture of matter. And yet, unlike the proton, which is famously stable, and unlike the neutron, which is stable when tucked safely inside many atomic nuclei, the lambda does not stick around. It is unstable. Not unstable in the way a wobbly table is unstable, or in the way I become unstable when someone explains a password policy for the third time, but unstable in a very specific physical sense. It is a real, valid particle. It can be created. It has identifiable properties. It can be tracked through the traces it leaves behind. But once it exists, it is already on borrowed time. That phrase borrowed time is a bit dramatic, but particle physics does occasionally invite drama. Not because the particles themselves are emotional, though one is sometimes tempted to assign them personalities, but because their behaviour can feel so brief and decisive. The lambda does not slowly fade or become tired of being itself. It decays. It transforms into other particles according to the rules allowed by nature. That is what unstable means here. Its internal arrangement, while perfectly possible, is not the final resting place. The universe permits it, but only temporarily. For a short interval it is there, with mass, spin, and a measurable identity. Then the arrangement gives way, and the ingredients reorganize into something else. That may sound alarming at first, but instability in the particle world is not a defect. It is not a sign that something has gone wrong. In fact, unstable particles are one of the main ways physicists learn what the universe is made of and how its forces operate. If every particle were stable forever, the subatomic world would be much quieter and much harder to understand. Decay gives us clues. Transformations leave trails. The products of a decay tell us what kinds of processes were possible and which rules were respected along the way. In that sense, instability is not merely a disappearance, it is a confession. The lambda vanishes, yes, but it leaves behind a statement about the hidden grammar of matter. There is also something quietly useful in remembering that many of the universe's most informative things are short-lived. We often assume importance should correlate with duration. Mountains last a long time, so they feel significant. Civilizations endure for centuries, so we grant them weight. A particle that survives only for an incredibly tiny instant sounds at first like a cosmic footnote. But the universe is not especially sentimental about duration. Some of its deepest truths flash by quickly. Some of its most revealing structures only exist in conditions we have to build carefully in laboratories or infer from the aftermath of collisions. The lambda particle is one of those cases where brevity does not mean insignificance. Quite the opposite. Its short life is part of the story. Its instability is not just a feature listed in a catalogue, it is central to why the particle matters at all. To appreciate that properly, it helps to loosen our grip on the everyday idea of what a particle is. In ordinary language, the word particle suggests something tiny and solid. A speck, a grain, a minuscule bead of stuff. That picture is not entirely useless, but it can become misleading rather quickly. Subatomic particles are not little marbles tucked inside matter, waiting to be poured out like sugar from a packet. They are excitations of fields, participants in interactions, entities whose properties are sharply defined in some ways, and deeply non-classical in others. They can be counted and categorized, yes, but not in the manner of pebbles in a jar. When physicists speak about a particle like the lambda, they are not describing a tiny billiard ball with a sulky temperament. They are describing a specific pattern the universe can support under the right conditions, a pattern made from quarks held together by the strong interaction, endowed with particular measurable traits and destined to transform through another interaction before very much time has passed at all. That sounds more technical, though perhaps less cuddly. Particle physics is not always cuddly. Still, one of the nice things about the lambda is that it sits right at the border between the familiar and the strange. It is not part of the stable matter making up your hands or your cup of tea, but it is built from quarks just as protons and neutrons are. It belongs to the same wider framework called the Standard Model, that grand and impressively successful catalogue of the known fundamental particles and the ways they interact. Within that framework, the Lambda carries a special distinction. It contains one type of quark that pulls it away from the more familiar proton and neutron story, and into a category that physicists historically described with a wonderfully evocative word: strange. That word strange in physics has one of those delightful histories where a technical label still preserves the mood of the discovery. Scientists were finding particles in cosmic ray events and high-energy collisions that behaved in an awkwardly puzzling way. They seemed to be produced readily enough by one interaction, and yet decayed more slowly than expected by another. That mismatch felt odd. They were not impossible, but they were surprising. So the word strange attached itself first to the behaviour and then to the quark involved. The Lambda particle contains a strange quark, and that single ingredient changes the character of the whole particle. It is still a baryon, still a three-quark object, still part of the same larger family as the proton and neutron, but it is not built from only the lightest and most familiar quarks. It carries strangeness in the historical, technical sense, and with that comes a different set of possibilities and a built-in path toward decay. This, by the way, is one of the places where particle physics becomes unexpectedly human. We give the deepest components of reality names like up, down, strange, charm, beauty, and truth. Though beauty and truth have since been more commonly called bottom and top in many contexts, perhaps because even physicists occasionally decide things are getting a little too lyrical. There is something endearing about this. The mathematics can be fierce, the experiments enormous, the concepts subtle, and yet the vocabulary sometimes sounds as though the universe is being catalogued by people who are sleep-deprived but trying their best to remain cheerful. In the midst of all that, the Lambda quietly keeps its role as a particle whose identity is tied to one strange quark and two lighter companions, a compact little arrangement with a very brief future. When I say brief, it is worth pausing for a moment over just how different particle timescales are from our own. We live among seconds, hours, years. Even our shortest everyday experiences have room for anticipation. You can wait for toast, you can regret sending a message, you can stare at a microwave as if personal disappointment might somehow reduce the remaining cooking time. Particles are not operating on that scale. The Lambda exists for a tiny fraction of a second before decaying. Yet in the subatomic realm, that is not nothing. It is enough to travel a measurable distance when moving quickly. It is enough to leave evidence. It is enough for a detector to catch the consequences. In particle physics, short-lived does not mean unobservable. Often it means one must be clever, and cleverness has always been part of this story. Nobody has ever sat quietly with a Lambda particle in the palm of the hand and had a good long look at it, which is frankly rude of the Lambda but understandable. What physicists do instead is create conditions where such particles can appear, then build detectors capable of recording tracks, energies, and decay products with extraordinary precision. From those traces they infer what must have been present before the decay occurred. This is one of the reasons the field can seem almost detective-like. The most interesting character in the drama may be gone before the audience realizes it has entered, and yet the evidence is enough to reconstruct the scene. That detective quality is especially important with unstable particles because they force us to think in terms of transformation rather than permanence. At school we often learn science by classifying things as though each object sits quietly in its designated box. Here is a solid, here is a liquid, here is a mammal, here is a planet. Particle physics does involve classification, and a lot of it, but those categories are inseparable from processes. A Lambda particle is not just a thing, it is a thing that can be made, identified, and then watched vanishing into other things. Its meaning lies partly in its relations, in the channels by which it can be created and the routes by which it can decay. It is a noun with a built-in verb. There is, I think, something deeply satisfying about that once one gets used to it. The world at its deepest known level is not made of static building blocks, stacked one atop another like a toy castle. It is made of entities whose identities are tied to interactions, probabilities, and permitted changes. Stability exists, certainly. The proton is an excellent example of staying power, but instability is just as fundamental. The lambda particle helps remind us that matter is not only about what persists, it is also about what can briefly be. And briefly be is such an important phrase here because it captures the peculiar dignity of the lambda. It is not a failed proton. It is not an incomplete neutron. It is its own particle, with its own mass, its own internal structure, its own historical importance, and its own role in teaching us how quarks behave when bound together by the strong force. For a short while, nature says yes, this combination may exist. Then, just as decisively, nature says, and now it will become something else. To us that may feel abrupt. To the universe, it is simply business as usual. The opening question then is not merely what is a lambda particle, it is also what does it mean for something to be real if it is so fleeting. Physics gives a surprisingly firm answer. Real does not mean permanent. Real means it has measurable effects, reproducible properties, and a definable place in the network of natural law. By that standard, the lambda is entirely real. Its instability does not make it less so. In fact, the details of that instability are among the most concrete things about it. The fact that it decays in particular ways, on a particular timescale, while obeying certain conservation rules and reflecting the presence of a strange quark, all of that is part of what makes the particle scientifically solid, even though the particle itself is physically short-lived. So tonight we begin there, with a particle that exists long enough to matter and not long enough to settle down. A particle that belongs to the hidden zoo inside matter, yet points beyond the familiar residence. A particle whose very instability made it historically important because it hinted that the subatomic world contained more structure, more variety, and more rules than anyone had first assumed. The lambda is one of those scientific subjects that becomes richer the closer you look. At first it seems like an exotic side character. Then you realise it sits at the crossroads of several big ideas all at once. Quarks, the strong interaction, decay, strangeness, detection, the history of modern particle physics. All of them pass through this small and short-lived object. And perhaps that is part of the charm of physics in general. So often we begin with a narrow question and find a whole hidden landscape attached to it. Ask what a lambda particle is, and one does not receive a simple little label and a pat on the head. One ends up wandering toward the internal structure of matter itself. One begins to see that protons and neutrons are not the final layer, that quarks come in types, that some combinations endure while others do not, and that the universe is generous enough to permit both stability and transience as equally lawful expressions of its underlying order. That order, though, is not visible from the surface of daily life. You do not feel lambda particles passing through your errands. Nobody misses a train because of baryon structure, at least not in any directly satisfying way. Yet the deeper order is there all the same beneath the human scale, governing what matter can be. And if one follows the story carefully, the lambda becomes a very good guide because it is just close enough to the familiar to be understandable and just distant enough from it to be surprising. It is made of the same general stuff as ordinary nuclear matter, but arranged in a way that introduces strangeness and invites decay. It is a cousin from the same family who turns up in interesting circumstances, tells you something unexpected about your relatives, and then leaves before dessert. So let us ease further inward from here. We have met the lambda by name, given it its basic character, and admitted from the start that it is unstable for reasons that are not accidental, but deeply tied to its internal makeup. To understand that properly, we have to widen the view a little and look at the crowded inner population from which such a particle emerges, because once you step beneath the atom and start meeting the residents one by one, the lambda begins to make much more sense. If the lambda particle is going to make any proper sense at all, we need to spend a little time in the crowded interior world from which it comes, because one of the easiest mistakes in physics is to imagine the atom as the end of the story. It is not. It is the beginning of the smaller story, and once you step inside it, what first seemed tidy starts becoming busy rather quickly. At school, the atom is often presented as a neat little package. There is a nucleus in the middle, electrons around the outside, and there we are, apparently done. It is a useful first sketch in the same way that drawing a house as a square with a triangle on top is useful if one is 5 and the goal is optimism rather than architectural precision. The sketch is not wrong exactly, but it leaves out the plumbing, the wiring, the drafts, and the general fact that reality tends to be much more complicated than the classroom version. The atom, as it turns out, is not a final, indivisible bead of matter. The very word atom comes from an old idea that meant uncuttable, something beyond division, the smallest possible unit. The universe, with its usual dry sense of humour, eventually revealed that atoms are absolutely divisible in the scientific sense, and rather enthusiastically so. Electrons are one thing, protons and neutrons are another, and once physicists had learned enough to look properly at protons and neutrons, even those turned out not to be fundamental. They too have internal structure. They are made of quarks. So the atom is less like a final object and more like the front gate to a very large and somewhat noisy zoological park. That hidden zoo is not populated by animals, of course, though physicists have given its inhabitants such a colourful collection of names that one could be forgiven for expecting a gift shop at the exit. Instead, it is populated by particles, some stable, some unstable, some easy to detect, some frustratingly elusive, some common enough that the whole visible world depends on them, others so short-lived that they appear only under special conditions and vanish almost as soon as they have arrived. Once you know that, the lambda particle stops seeming like an isolated curiosity and starts looking like one resident among many in a wider population of possible matter states. It is not an accident. It is part of a pattern. Now, when physicists talk about a zoo of particles, they are not simply being whimsical, although they do enjoy that sort of phrase. They are trying to capture the sheer number of distinct entities that showed up once experiments became powerful enough. In the early days of atomic physics, the cast of characters seemed manageable. There were electrons, protons, later neutrons, and for a little while it looked as though perhaps nature had shown its hand, and the deck was mercifully small. Then the 20th century continued, and nature did what it often does when humans begin feeling confident. It produced more particles, then more. Then an entire spread of particles appearing in cosmic rays and accelerator experiments, each with its own mass, charge, lifetime and behaviour, until the whole business began to resemble a taxonomic crisis. There is something almost comical about that period in hindsight. Physicists were not discovering the clean, elegant minimalism they had perhaps hoped for. They were finding a growing parade of strange, short-lived objects with names, lifetimes, and decay patterns that had to be tracked carefully. One can imagine the mood shifting from triumphant curiosity to something slightly more clerical. Ah, yes, another particle. Better get a notebook. But that apparent mess was not the sign of a broken theory. It was the sign that deeper structure was waiting underneath, just as a large number of chemical substances eventually made more sense once one understood atoms and the periodic table. The particle zoo looked unruly before its order was understood. Then quarks entered the picture, and many of those animals, if we continue the zoological metaphor longer than strictly necessary, turned out to be built from a smaller set of more fundamental ingredients. Before getting to quarks properly, though, it helps to slow down and separate the main residents of the subatomic world into a few broad families. This matters because the lambda particle belongs to one of them, and the differences between these families tell us a great deal about how matter is assembled. At the broadest level, there are particles that make up matter and particles that carry forces. This is not the whole story, but it is a useful way in. Matter particles include quarks and leptons. Force carriers include things like the photon for electromagnetism and the gluon for the strong interaction. There are also the more famous and rather important gauge bosons associated with other forces, and then there is the Higgs boson, which occupies its own crucial niche in the modern picture. The atom you learned about in school is built primarily from electrons on the outside, and protons and neutrons in the centre. Electrons are leptons. Protons and neutrons are not fundamental at all but composite particles built from quarks. The electron, for all its long history in science, remains one of the simplest known matter particles in the sense that it appears fundamental. It has electric charge, it has mass, it has spin, and so far no internal structure has been found. You do not open an electron and discover smaller luggage packed inside. It simply is what it is. That already sets it apart from the proton and neutron, which are much less elementary than they first appeared. For many years, protons were treated almost as if they were fundamental building blocks, reasonably so. They sit at the heart of every ordinary atomic nucleus, positively charged and reassuringly substantial compared with the featherweight electron. Yet when experiments began probing them at high energies, the proton ceased to look simple. It had parts. The neutron did as well, and those parts were quarks. This is where the hidden zoo becomes especially interesting, because quarks themselves are never found wandering about alone in ordinary conditions. They are confined. They come bound together in combinations held by the strong interaction. This is one of the deepest and strangest features of particle physics. If you ask what ordinary visible matter is made of, the answer quickly becomes quarks and electrons. But if you then ask to be shown a lone quark sitting politely on a tray, nature refuses. Quarks exist. Their properties are measurable. Their effects are everywhere in hadrons. And yet they do not present themselves as isolated specimens in the way an electron can. It is as if the universe were perfectly happy for you to infer them, calculate them, depend on them, and even build an entire theory around them, but not to invite one out individually for tea. The combinations quarks form fall into categories. One very important category consists of particles made from 3 quarks. These are called baryons. The proton is a baryon, the neutron is a baryon, and, importantly for us, the lambda particle is a baryon too. There is another major category made from a quark and an antiquark together. These are mesons. Both baryons and mesons belong to a larger class called hadrons, meaning particles that feel the strong interaction in the sense relevant here. So when we speak about the hidden zoo inside the atom, we're not speaking only of the familiar proton and neutron. We are speaking of a much larger set of hadrons, many of which exist only briefly, many of which were discovered in high-energy experiments, and many of which make sense once quarks and their combinations are understood. One of the reasons this felt like a zoo historically is that the hadrons came in such abundance. There were particles with different masses, different charges, different lifetimes, different decay patterns, and initially it was not obvious why nature should allow so many. The answer was not that each one was an entirely separate fundamental ingredient. Rather, many were composite arrangements built from quarks in different combinations, much as many chemical molecules can be built from a smaller set of atomic elements. Once that idea took hold, the zoo began to look less like chaos and more like a catalogue. Even so, it remains a fairly lively catalogue. Quarks themselves come in types, or flavours, as physicists charmingly insist on calling them, which makes particle physics sound for brief moments like a very intense ice cream menu. The lightest and most familiar are the up and down quarks. The proton is made of 2 up quarks and 1 down quark. The neutron is made of 2 down quarks and 1 up quark. Already that is lovely in its economy. Change one ingredient and you shift from proton to neutron. That alone tells you something profound. Matter is sensitive to composition at the deepest level. Small differences in internal arrangement can produce particles with different properties and different roles in the universe. But up and down are not the whole story. There are also strange, charm, bottom and top quarks. These heavier flavours open the door to an enormous range of less familiar hadrons. Some of those particles can be created in collisions when enough energy is available. and they often decay rapidly into lighter particles. The lambda particle enters right there, because unlike the proton and neutron, it contains a strange quark. That single fact places it in the wider hadron zoo beyond ordinary nuclear matter. It is not made only from the mild everyday ingredients that dominate the atoms around us. It includes one quark of a type that does not show up in stable ordinary matter, at least not in free-lasting combinations around the room. That is why the lambda belongs to a more exotic but still deeply lawful population of particles. The strange quark deserves a little patience because the name can make it sound theatrical, and perhaps a little suspicious, as though physicists found it lurking somewhere after hours. In truth, the label reflects a historical puzzle. Certain particles were produced in ways that suggested one kind of interaction, but decayed more slowly than expected in ways that suggested another. They had an odd pattern. Strange behaviour, in the technical and once rather colloquial sense, gave rise to the naming. The lambda was among the particles associated with this historical category, and so what looks at first like an exotic side road actually belongs to one of the main episodes in the development of modern particle physics. The strange particles helped force scientists to develop better organising principles and eventually a deeper quark-based understanding. There is another important distinction inside this zoo, and it concerns stability. Some particles are stable, or stable enough for all practical purposes. The electron appears stable. The proton appears stable to a staggering degree and has never been seen decaying, despite serious experimental efforts to catch such an event. The neutron, when free and alone, is unstable and decays after a modest lifetime by nuclear standards, though when bound inside many nuclei it can remain stable indefinitely as part of the larger arrangement. Other hadrons are much less patient. They decay quickly, some through the strong interaction itself, some through the electromagnetic interaction, others through the weak interaction. Those different routes matter because they help determine how long a particle survives and what it turns into. This is exactly the sort of thing that makes the hidden zoo feel less like a list and more like a society with strict rules. Particles are not merely objects, they are participants in processes. What can transform into what, how fast, and by which interaction are all governed by conservation laws and coupling strengths. Charge must be conserved. Energy and momentum must be conserved. Other quantum numbers are conserved in some interactions and not in others. Once physicists understand these rules, the apparent chaos of many particle types becomes much more intelligible. The zoo has signage after all. It just took a while to read it. Inside the atom as we usually encounter it, protons and neutrons are the only hadrons that remain around long enough to build stable nuclei. They are, if you like, the dependable residents of the neighbourhood, but they are not the only baryons nature allows. They are simply the ones that ordinary low-energy matter settles into. Under higher energy conditions, many other baryons can appear. Some are heavier cousins, some contain strange quarks, or charm quarks, or other heavier flavours. The lambda is one of the lightest strange baryons, which makes it particularly important. It is not so heavy or so remote from ordinary matter that it becomes purely arcane, yet it is different enough to reveal what happens when the internal recipe of a baryon includes strangeness. If that sounds a bit like cooking, I do apologise, though particle physics often tempts one into culinary language. The combinations matter, the ingredients matter. The final behaviour depends on the recipe. The difficulty, of course, is that in this kitchen the ingredients are quarks, the utensils are fundamental interactions, and the meal generally vanishes before one has properly set the table. Still, the analogy has some use. A proton and a neutron are not random lumps. They are specific arrangements, so is a lambda. And once you admit that baryons can come in different quark combinations, the hidden zoo inside the atom stops feeling mysterious in the bad sense and starts feeling structured in the satisfying sense. There is also the strong interaction itself, which deserves to be treated as more than a background detail because it is the reason baryons and mesons exist at all. The strong interaction is carried by gluons and binds quarks together. It is extraordinarily powerful at the scale of hadrons. Without it, quarks would not form protons, neutrons, lambdas, or any other hadrons. More dramatically still, without it there would be no stable atomic nuclei in the familiar sense, no chemistry, no planets, no teacups, and certainly no late-night reflections on particle physics. It is one of those cases where the invisible infrastructure of reality turns out to be doing nearly all the heavy lifting, and yet the strong interaction does not simply glue anything to anything in any way it likes. It is rule-bound. Quarks carry a kind of charge known as colour charge, though the word colour here has nothing to do with visual colour and everything to do with physicists enjoying slightly misleading terminology. Quarks combine in ways that produce colour-neutral objects. Baryons do so with 3 quarks. Mesons do so with a quark and an antiquark. The resulting hadrons are the colour-neutral objects we can observe. This explains why the zoo has families and patterns rather than total anarchy. Deep rules are shaping the possible residents. The atom therefore hides more than just empty space and a compact nucleus. It hides a whole theory of matter in layers. At the outer layer, the electrons set the stage for chemistry. In the nucleus, protons and neutrons define the identity and stability of the atom itself. Within the proton and neutron, quarks move in a strongly interacting system that is anything but static. The proton is not 3 little marbles sitting still in a triangular arrangement, like polite schoolchildren awaiting instruction. It is a dynamic quantum object full of quarks, antiquarks, and gluons in ceaseless interaction. The same is true in a broader sense for other baryons, so when we imagine the inside of matter, the truth is much busier than the simplified textbook picture. It is not a still life, it is a managed storm. That managed storm gives rise to the zoo. Different configurations are possible. Some are long-lived, some are short-lived. Some appear naturally in energetic cosmic events or in particle accelerators. Some can be studied through the tracks their decay products leave behind. And through all of this, the idea of a particle becomes richer. A particle is not simply a tiny fixed object. It is a stable or unstable excitation with particular properties emerging from the underlying quantum fields and interactions. That may sound more abstract than a simple ball-bearing model, but it is more faithful to what experiments reveal. The hidden zoo is not a cupboard of little pebbles. It is a catalogue of allowed quantum arrangements. This is also the point at which one begins to appreciate why the lambda particle matters enough to deserve its own careful discussion. It is not merely another name on a long list. It sits at an interesting intersection. It is a baryon, so it belongs with the proton and neutron as a 3-quark object. It contains a strange quark, so it points beyond ordinary nuclear matter into the realm of strangeness. It is unstable, so it helps reveal how certain particles decay, and which interactions govern that decay. It is light enough among strange baryons to have historical and conceptual importance. In short, it is one of the most accessible doors into the deeper hadron zoo. One might reasonably ask why the universe allows such a zoo in the first place. Why not just a few particles and be done with it? This is not a silly question. In fact, it hovers behind much of modern physics. Why these particles, these masses, these interactions, these combinations? Some answers we have in practical terms. The Standard Model describes the known particles and interactions with tremendous success. It tells us what combinations are possible, what processes occur, and what probabilities to expect. Yet, on the deeper, why there remains room for philosophical restlessness. Nature does not seem obliged to be minimal in the way human aesthetics might prefer. It allows a spectrum of particles, many short-lived, many heavy, many appearing only in energetic conditions. The zoo is real whether or not it flatters our taste for simplicity. What does flatter our taste, at least a little, is that the zoo turned out not to be fundamental chaos. Once quarks and the relevant symmetries were understood, order emerged from the clutter. Particles could be grouped, patterns could be predicted, new states could be anticipated before discovery. This was one of the great triumphs of 20th century particle physics. the bewildering collection of hadrons began to resemble a coherent family tree. The lambda found its proper place in that tree, not a random oddity, but a lawful composite particle with a definite quark content and a characteristic way of behaving. So when we speak of the hidden zoo inside the atom, we're really speaking about a change in perspective. The atom is no longer the tiniest endpoint. The nucleus is no longer the deepest level. Protons and neutrons are no longer indivisible. Instead, we find layers of structure, categories of particles, families of combinations, and interactions that both permit and constrain the forms matter can take. The lambda belongs to that deeper world, a world that is hidden not because it is mystical, but because it lies beneath direct human perception and had to be uncovered by experiment theory and a frankly heroic amount of patience. And once you begin to see that hidden world properly, ordinary matter starts to look a little different. The solid world around you is no less real, but it becomes more astonishing. Everything stable around us is built upon rules that also allow transience. The durable proton shares its broader baryonic identity with unstable cousins like the lambda. The quiet nucleus inside the atom is linked conceptually to a much wider population of possible hadrons. Reality, in other words, is not composed only of the forms that happen to last long enough to build furniture and planets. It also includes a whole hidden cast of temporary arrangements, each of them lawful, each of them revealing something about the machinery underneath. That is why the zoo matters. It tells us that matter is richer than the everyday world suggests, and it prepares us for the next step, because once the crowd inside the atom has come into view, the lambda no longer appears as an isolated exotic name. It appears as a specific resident with a definable address, a 3-quark baryon carrying strangeness, familiar enough in family to be understandable, and unusual enough in composition to open the real question waiting underneath all this, namely what the lambda particle actually is when you look at its internal makeup directly. Now that the wider particle crowd is in view, we can move closer to the lambda itself and answer the question in a more direct way, because it is one thing to say that the lambda particle belongs to the hidden zoo of hadrons, and another to say plainly what it is. A lambda particle is a baryon made of 3 quarks. More specifically, the most commonly discussed lambda particle is built from 1 up quark, 1 down quark, and 1 strange quark. That is its basic internal composition. Those 3 quarks are bound together by the strong interaction, held in a compact quantum state that gives the particle a definite mass, a neutral electric charge, a particular spin, and a very short lifetime before it decays into lighter particles. That simple description is already doing quite a lot of work. It tells us the lambda is not fundamental in the way the electron appears to be. It tells us the lambda is a composite particle, something assembled from more basic ingredients. It tells us it belongs to the baryon family, which means 3 quarks rather than a quark paired with an antiquark, and it tells us it contains a strange quark, which places it outside the narrow set of particles making up ordinary long-lived matter around us. A proton and a neutron are also baryons, but they are built only from up and down quarks. The lambda is what happens when the family resemblance remains but the recipe changes. That change matters because particles are not defined only by being small, they are defined by their measurable properties, and those properties emerge from the specific combination and arrangement of their constituents. If you were to hear that the proton is made of 2 up quarks and 1 down quark, and the neutron is made of 2 down quarks and 1 up quark, you might initially think that switching 1 quark for another is a minor adjustment. It is not. That small change can alter the particle's electric charge, its mass, its stability, and its role in the world. In exactly the same way, when the lambda replaces one of the lighter quarks one might find in an ordinary baryon with a strange quark, the result is not merely a proton or neutron in unusual clothing. It is a distinct particle with its own identity. The first thing to keep in mind is that the lambda is electrically neutral. That can surprise people a little, because strange particle often sounds as though it ought to come with some dramatic charge attached, perhaps for branding purposes if nothing else. But no, the ordinary lambda is neutral. The charges of its 3 quarks add up to 0. This means that in terms of electric charge, it resembles the neutron rather than the proton. Of course, similarity in one property does not imply they are otherwise the same. The lambda is heavier than the neutron, and crucially it contains a strange quark rather than only up and down quarks, so the resemblance is limited. Still, this neutral character is part of the lambda's fingerprint. It belongs among the identifying facts that physicists use to distinguish one particle from another. The next important property is that the lambda has spin. In the language of particle physics, spin is a fundamental angular momentum-like property built into the particle's quantum nature. It does not mean the lambda is literally spinning like a toy top in a tiny invisible room. That image is charming but misleading. Spin is a quantum property, not a little mechanical rotation in ordinary space. The lambda has the same overall spin category as the proton and neutron, which is one reason they sit in related parts of the hadron family tree. This matters because spin influences how particles behave, how they combine, and how they interact with one another. It is one of the deep labels that define what sort of entity a given particle is. Then there is the mass. The lambda is heavier than the proton and neutron, and that is exactly what one should expect when one of the constituent quarks is strange rather than up or down. The strange quark is more massive than the up and down quarks, and that extra mass contributes to the total mass of the lambda. Strictly speaking, with hadrons, one must always be careful not to think of the total mass as a simple, household sum of 3 ingredient labels added together in the corner of the kitchen. Much of the mass of hadrons comes from the dynamic energy of the strong interaction that binds the quarks, not just from the bare masses of the quarks themselves. Even so, the presence of a strange quark helps make the lambda significantly heavier than the more familiar proton and neutron. That greater mass is part of what makes the lambda unstable. It is not the whole explanation, but it is part of the landscape. Because the lambda is heavier than the particles into which it can decay, there is room for transformation. Nature is not required to preserve the lambda's specific form indefinitely. The strong interaction can create it under the right conditions, but when the time comes for it to decay, the weak interaction is typically involved in changing the strange quark into something else, and the lambda becomes lighter particles. We will get into that mechanism in detail later. For now, what matters is that the lambda is a valid but temporary arrangement. Its internal composition gives it a real identity, but not a permanent one. This is a good place to pause over the idea of identity, because in particle physics, identity is not based on visual appearance, and certainly not on any kind of texture, shape, or colour in the ordinary sense. A particle is what it is because of a collection of quantum properties: mass, charge, spin, quark content, lifetime, decay channels, and interaction behaviour all belong to that identity. When physicists say they have identified a lambda particle, they do not mean they found a tiny object with the word lambda written on the side in very small but courteous lettering. They mean they found evidence for a particle with the right set of measurable characteristics, often reconstructed from what it decayed into and how those decay products behaved in a detector. So what is the lambda actually? It is a specific quantum state of 3 quarks, one up, one down, and one strange, bound by gluons through the strong interaction into a neutral baryon with a defined mass, spin, and lifetime. That is the clean answer. But clean answers in particle physics nearly always hide a richer mess behind them, and the lambda is no exception. For one thing, the 3 quarks in a baryon are not sitting still. It is very tempting to picture them as 3 tiny coloured balls in a little cluster, perhaps vibrating slightly as though they have had too much tea. Real hadrons are much less tidy. The lambda is a quantum object. Its quarks are part of an interacting system full of motion, exchange gluons, and the deeper structure described by quantum chromodynamics, the theory of the strong interaction. The lambda is not 3 hard beads glued together. It is a bound state in a quantum field theory, and that means its internal life is dynamic in a way that resists simple, visual analogy. Even the phrase bound state is worth dwelling on. It means the constituents are held together by an interaction strong enough to produce a stable, or at least temporarily stable, composite system. In the case of the lambda, the strong interaction binds the quarks so firmly that they do not appear separately. You do not see an up quark floating a bit to the left of the lambda and the strange quark having a quiet moment by itself on the right. The baryon is the thing you get. The individuality of the quarks is real in terms of their quantum numbers and theoretical description, but the observed object is the bound state as a whole. This is why baryons occupy such an interesting place in physics. They are not elementary, but they are also not casual collections. A bicycle left in pieces in a hallway is not a bicycle in any satisfying sense. A baryon, by contrast, is not a mere pile of quarks. It is a tightly organised quantum state. The whole has definite properties that belong to the bound system. The lambda is one such whole, and when we ask what it actually is, we should resist both extremes. It is not an indivisible elementary particle like the earliest atomists hoped all matter might be, and it is not a loose bag of 3 ingredients rattling around. It is a structured, specific, short-lived composite particle. There is another subtle point that matters here. The lambda is not just any 3-quark combination containing one strange quark. There are other baryons that also contain strange quarks, and they are not all the same. The way the quarks combine, including the symmetry properties of their quantum state, affects which particle results. This is part of why the hadron family tree is so rich. Quark content is crucial, but it is not always the whole story. There can be distinct particles with related ingredients but different overall configurations. The lambda occupies a definite place among these possibilities, and that place is one of the reasons it became historically important. It was not merely some generic, strange baryon. It was a specific one with a recognisable pattern of production and decay. To appreciate that, it helps to think of particle identity as something closer to a musical chord than a sack of notes. If I may borrow one analogy and then promise not to get carried away with it, 3 notes played together can produce very different musical results depending on arrangement and relation. Likewise, 3 quarks can form distinct hadronic states, depending on how their quantum properties line up. The lambda is one definite chord in that baryonic repertoire. The ingredients matter, but so does the structure of the whole. Historically, the lambda was important because it belonged to a set of particles that seemed odd in their behaviour. They could be created in high-energy collisions through the strong interaction, which happens quickly, but they decayed more slowly than strong interaction decays usually would. That mismatch was one of the clues that led physicists to recognise that another kind of hidden property was involved, what came to be called strangeness. In modern quark language, this became much easier to understand. The lambda contains a strange quark. Strong interactions can produce strange quarks in appropriate combinations, but when a strange quark needs to change into a different flavour for a decay to happen, the weak interaction is involved, and that process is slower. The lambda's identity is therefore tied not only to what it is made of, but to how the universe permits that composition to change. You can almost think of the lambda as a sort of bridge particle. It stands between the ordinary matter we know best and the wider strange sector of hadron physics. It is not so exotic that it has nothing to do with the familiar proton and neutron. On the contrary, it is built according to the same broad baryonic logic. But it is not ordinary either. The strange quark changes the entire tone of the particle story. It changes the mass. It changes the available decays. It changes the historical role the particle played in the development of theory. It makes the lambda a wonderful example of how one deeper ingredient can alter a whole physical identity. There is something quite elegant in that. In everyday life, we're used to object categories being blunt. A chair is a chair, unless it is broken, in which case it is either a broken chair or modern art depending on the room. At the particle level, categories are more exact and more delicate. A difference in constituent content or quantum arrangement creates a genuinely different entity. There is no room for saying, well, this is basically a neutron in spirit. Nature is not grading on effort. The lambda is what it is because of its full physical definition, and that definition is precise. Now, if the lambda is real and well defined, why is it not part of ordinary matter? The reason is that ordinary matter settles into the most stable available configurations under normal conditions. Stable nuclei are made from protons and neutrons. Atoms surround those nuclei with electrons. The lambda, being heavier and unstable, does not remain as a common ingredient of ordinary material objects. It can be produced in energetic processes, in particle collisions, in cosmic ray interactions, and in certain nuclear environments, but it does not stick around long enough to build tables, moons, or respectable filing cabinets. It is part of the universe's allowed vocabulary, but not part of its everyday long-form prose. That does not make it marginal. In fact, the very fact that the lambda is not part of everyday stable matter is one of the reasons it teaches us so much. Stable objects tell us what the universe settles on. Unstable ones tell us what the universe allows on the way. The lambda is one of those allowed arrangements that reveals the rules of assembly and decay. It tells us that 3 quark baryons can include strangeness. It tells us that such a baryon can be created readily enough through strong processes, and it tells us that its later transformation is governed by the weak interaction. That is a rather impressive amount of information for one short-lived particle to carry. It is also worth noting that the lambda is not purely a theoretical book entry. It is observed, it is measured, it shows up in experiments and in the products of high-energy interactions. Physicists know its mass, its lifetime, and its common decay modes because these have been studied with great care. One of the beautiful things about particle physics is that even things too small and too brief to be seen directly in any ordinary sense can still be known with extraordinary precision through the pattern of evidence they leave. The lambda is not visible in the way a grain of sand is visible, but its presence is written into detector data with enough consistency that its identity becomes unmistakable. This also helps answer a common intuition problem. People sometimes hear that a particle is unstable and imagine that perhaps it is vague or uncertain in a hand-waving sense. Quite the opposite. The lambda's instability is itself a sharply measurable feature. Its lifetime is not a sign of imprecision. It is part of the precision. Nature gives the lambda a particular statistical tendency to decay after a certain characteristic interval. Not every individual lambda waits exactly the same duration in some clock-like way, because quantum decay is probabilistic, but across many events the pattern is definite and reproducible. So even the fact that the lambda does not last becomes part of what defines it. There is a philosophical comfort in that if one is in the mood to find comfort in subatomic matters, which I admit is a specialized hobby. A thing need not last to be exact. It need not persist to have identity. The lambda exists briefly, but while it exists, it is itself in a fully lawful, physically meaningful way. Then it decays. The story continues, and the evidence remains. So when someone asks what a lambda particle actually is, the answer is not a vague gesture towards something tiny and unstable. It is a specific neutral, strange baryon, made of one up quark, one down quark, and one strange quark, bound by the strong interaction into a definite composite particle that is heavier than the proton and neutron, and decays through the weak interaction after a short lifetime. It belongs to the hadron family. It is one of the lightest strange baryons. It played a key role in the historical path toward understanding strangeness and quark structure, and it remains an important object for studying how matter behaves when one steps beyond the most familiar and stable forms. From here, the next natural step is to focus more closely on that one ingredient that changes everything. Because if the proton and neutron are built from up and down quarks, and the lambda becomes distinct the moment a strange quark enters the arrangement, then the real turning point in the story lies with strangeness itself. Once that strange quark is given its due, the lambda stops seeming merely unusual and starts looking like exactly the particle it had to be. The moment the lambda particle becomes more than just another unfamiliar name is the moment the strange quark enters the picture, because that is where the entire tone of the story changes. Up to that point, one could almost imagine the subatomic world as a somewhat manageable household built from electrons, protons, neutrons, and then, with a little more courage, from up and down quarks. It is already a remarkable picture, but still one that feels modestly domestic by the standards of modern physics. Then strangeness arrives, and the universe politely informs us that it has more categories than we first supposed, more patterns than everyday matter reveals, and a very particular sense of humour when it comes to naming things. The strange quark is one of the 6 known quark flavours. That is the official language, flavours, which continues to sound as though particle physics should be discussed with a spoon in hand, but one learns to accept these things. The 6 quark types are up, down, strange, charm, bottom, and top. Of these, up and down are the lightest and most familiar in the sense that they build the ordinary baryons we meet first, the proton and neutron. Strange is the next step away from that familiar territory. It is heavier than up and down, and because of that, and because of how the weak interaction treats it, the presence of a strange quark inside a hadron changes both the mass of the particle and the ways it can decay. Now, saying that a quark is strange does not mean it behaves like an eccentric neighbour with unconventional opinions about gardening. In modern particle physics, strange is just the name of a flavour, one category of quark among the 6. But the historical reason that word became attached to it matters a great deal, because it was not chosen at random. It emerged from a genuine puzzle in experiments, a puzzle that helped reshape how physicists thought about subatomic particles. The birth of strangeness as a concept came before the full quark model was established. Scientists first noticed certain particles whose behaviour seemed oddly split between 2 different tempos. These particles were produced quickly, as though the strong interaction were responsible, but they decayed comparatively slowly, in a way that suggested the weak interaction was doing the final work. That mismatch looked peculiar. Not impossible, just peculiar enough to demand explanation. To appreciate why that was so puzzling, it helps to remember that the strong interaction and the weak interaction operate very differently. The strong interaction is, as the name suggests, very strong at short distances and is responsible for binding quarks into hadrons. Processes governed by it happen extremely quickly. The weak interaction, on the other hand, is much weaker and is responsible for certain kinds of particle decay, including flavour changes that the strong interaction does not permit. Weak decays are slower by particle physics standards. So when physicists began seeing particles that seemed easy enough to create in energetic collisions but unexpectedly slow to decay, they had the distinct feeling that nature was giving them 2 contradictory hints at once. This happened especially in studies of cosmic rays and later in accelerator experiments. Before giant colliders became the standard machinery of particle discovery, cosmic rays were one of the main windows into high-energy phenomena. Particles from space, striking the atmosphere and producing showers of secondaries, gave physicists glimpses of short-lived and unusual objects. Among those objects were particles that did not fit comfortably into the earlier, simpler picture of matter. They had masses and decay patterns that distinguished them from protons, neutrons, and pions, and they often appeared in pairs or in ways that suggested some hidden bookkeeping rule was at work. That hidden bookkeeping rule became the key idea. Physicists began to suspect that these odd particles carried some new property, conserved in the processes that produced them, but not necessarily in the processes that destroyed them. This was a very clever move conceptually. Instead of treating each new particle as an isolated nuisance, they looked for a pattern linking them. The result was the introduction of a new quantum number called strangeness. This number was assigned to particles in such a way that strong interactions conserved it. That meant strange particles had to be produced in combinations that balanced the total strangeness. But weak interactions could change strangeness, which meant those particles could later decay in ways that did not preserve it. This idea brought order to what had looked like an awkward mess. Suddenly, the strange particles were not just miscellaneous oddities. They belonged to a coherent category. They were being born through one set of rules and dying through another. The strange quantum number explained why they tended to be produced in associated ways and why they lived longer than a particle created and destroyed purely by strong interactions would be expected to live. The Lambda particle fit beautifully into this emerging pattern. It was one of the particles carrying strangeness, and its behaviour reflected exactly the kind of two-tempo life that had caused all the fuss in the first place. There is something elegant about this stage of science. Before anyone had a full quark-based picture, they had already begun to see that nature's apparent clutter could be organised by hidden symmetry and conservation laws. This often happens in physics. A pattern becomes visible before the mechanism underneath it is fully understood. You first notice that certain outcomes repeat, certain combinations appear, certain transformations are allowed while others are absent, and from that you infer that some deeper rule must be at work. Strangeness was one of those rules. It was a label for regularity before it became a clue to internal structure. Only later, with the development of the quark model, did that internal structure become much clearer. In the quark picture, strangeness is tied directly to the presence of the strange quark. A hadron containing one strange quark carries strangeness in the corresponding sense. The Lambda particle, with one up quark, one down quark, and one strange quark, is therefore a strange baryon. The quark model gave a concrete basis to what had previously been a more abstract classification scheme. The hidden bookkeeping was no longer just bookkeeping. It reflected actual constituent content. This was a major conceptual step. Once quarks entered the story, many of the hadrons in the old particle zoo suddenly looked far less mysterious. Instead of dozens of unrelated residents appearing to have wandered into the experimental record by accident, there was now a smaller set of underlying ingredients that could combine in lawful ways. Strange particles were those containing strange quarks. The Lambda was not merely odd. It was a baryon whose composition included one of these heavier flavours. The word strange remained, but it now pointed to something quite precise. And yet the historical flavour of the word remains worth remembering, because it captures a real moment in science when nature seemed to be misbehaving according to old expectations. That feeling of slight irritation followed by deep satisfaction is one of the most reliable engines of progress in physics. A result refuses to fit. A category needs expanding. A new conservation law appears. A deeper model replaces the old one. One can almost imagine the conversation in broad outline. These particles are being produced too easily to be rare accidents. Yes, but they are decaying too slowly for strong processes. Then perhaps we need a new property. And so strangeness enters not as poetry, but as disciplined confusion resolved by better theory. The strange quark itself in the modern standard model is not mysterious in the supernatural sense. It is one member of the quark family, carrying the same magnitude of electric charge as the down quark, but with greater mass and different flavour identity. Like all quarks, it interacts through the strong interaction. Like other quarks, it participates in weak interactions as well, and those weak processes allow it to change into other flavours under the right circumstances. This ability to change flavour through the weak interaction is central to why strange hadrons such as the Lambda are unstable. The strong interaction may bind the strange quark into the baryon, but it does not remove the possibility of a later weak decay in which the strange quark transforms and the whole particle becomes something lighter. This interplay between strong binding and weak decay is one of the most important themes in the Lambda's story. The Lambda is not unstable because the strong interaction fails to hold it together. On the contrary, the strong interaction is what makes the Lambda a real hadron in the first place. The instability comes because the strong interaction is not the whole story. A strange quark embedded in a baryon can be changed by the weak interaction into a lighter quark, and once that happens, the baryon can no longer remain the same particle. So the presence of strangeness is not just a label. It is the reason the Lambda has a built-in root out of its own identity. That may sound rather existential for a particle, but the point is physical and precise. The proton contains only up and down quarks, and as far as we know, has no available simple decay route within the standard model that would make it vanish on observable timescales. The lambda, by contrast, contains a strange quark. That strange quark is heavier and can transform through the weak interaction. The result is a baryon that is perfectly allowed, perfectly real, but only temporarily so. Its internal composition includes a kind of instability, not because the particle is badly assembled, but because one of its ingredients belongs to a flavor sector that can evolve into lighter configurations. The birth of strangeness as a concept also fed directly into one of the great organizing achievements of particle physics, namely the use of symmetry patterns to classify hadrons. Once physicists had several strange and non-strange hadrons catalogued, they began to notice groupings and regularities among them. These patterns eventually contributed to classification schemes that arranged hadrons into families according to shared properties. The lambda found its place among these families not as a random anomaly, but as part of a broader order, linking baryons with different charges, masses, and strange content. This was one of the signs that the particle zoo had deeper structure rather than mere overcrowding. There is an odd comfort in that. Human beings are generally tolerant of complexity so long as it eventually begins filing itself alphabetically. The Hadron Zoo was alarming when it looked like endless proliferation. It became much more welcome once it started obeying patterns. Strange particles were crucial in that transition. They forced the development of richer classification methods and helped point toward the Quark framework that would make the whole enterprise more intelligible. The lambda was therefore not just an interesting particle, it was part of a conceptual turning point. One should also say a word about how remarkable it is that experimentalists could make sense of any of this at all. Strange particles are not labelled at birth. They do not line up obligingly beneath a sign saying this one contains a strange quark. Their presence had to be inferred from tracks in detectors, from masses reconstructed out of decay products, from rates and lifetimes and production patterns. In the earlier days, this required an extraordinary amount of painstaking work. Bubble chambers and cloud chambers recorded tracks that had to be interpreted event by event, often from photographs, with each odd branching or displaced decay offering a clue. The lambda's story is not only one of theoretical insight, it is also one of experimental patience bordering at times on heroic stubbornness. A displaced decay, incidentally, is one of the lovely signatures associated with certain unstable particles. If a particle lives long enough to travel a short distance before decaying, the decay products appear to emerge not directly from the original collision point, but from a nearby secondary point. That little separation in space is like the particle leaving a note saying I was here briefly before turning into something else. Strange particles, including the lambda, often produce such signatures because their lifetimes were longer than those of particles decaying through the strong interaction, but still short enough to be unmistakably unstable. This helped experimentalists recognize that they were dealing with a distinct class of behavior. Once the strange quark became part of the accepted model, the old notion of strangeness found its natural place inside a much deeper theory. Quarks provided the constituent basis. Quantum chromodynamics described the strong interaction that bound them. The weak interaction explained flavor-changing decays. What had begun as an awkward empirical category became one piece of a coherent and predictive framework. The lambda, once strange in the historical sense, became understandable in the structural sense. It remained no less interesting for that. If anything, it became more so, because understanding does not reduce wonder nearly as much as people sometimes fear. It simply changes the flavour of the wonder. That is especially true when one remembers that the strange quark is not some decorative addition to the standard model. It belongs to a general pattern of quark families and flavour structure that remains one of the theory's most fascinating aspects. Why there are 6 quark flavours rather than 2 or 20 is still not answered at the deepest level. Why their masses take the values they do is not explained from first principles within the standard model itself. So even though strangeness became orderly in one sense, it still points to wider open questions. The lambda may be well understood as a hadron, Yet the existence of strange quarks at all continues to hint at a deeper story about how the particle world is arranged. For our purposes, though, the crucial thing is this. Strangeness was born as an attempt to explain a pattern of production and decay that did not fit older expectations. It became a formal quantum number that was conserved in strong interactions but not in weak ones. Later, the quark model grounded that idea in the existence of the strange quark, and the Lambda particle stands as one of the clearest examples of what all this means in practice. It is a baryon whose identity depends on containing a strange quark, and whose instability follows from the fact that this strangeness can be removed by weak decay. There is a very satisfying economy in that, even if it took a great deal of intellectual effort to discover. A puzzling category of particles appears. A new conserved quantity is proposed. A deeper constituent theory eventually explains that quantity in terms of actual building blocks. A particular particle, the lambda, sits right at the centre of the story, embodying the whole transition from mystery to mechanism. That is why the word strangeness deserves its place, not because it sounds delightful, though it does, but because it marks the moment when particle physics learned that the universe's apparent clutter might in fact be hiding a more elegant order than anyone first suspected. And once that idea took hold, the lambda was no longer merely one more strange particle in a growing list. It became something more specific and more illuminating, a case study in how new forms of matter are first noticed by their odd behaviour and only later understood by their internal structure. From there, the next step is naturally to watch the lambda move out of theory and into history, because after strangeness was named and recognised as a real feature of the particle world, the question became how physicists first caught the lambda itself and realised that this brief little baryon had indeed been hiding in the data all along. By the time the lambda particle began to emerge as a real scientific object rather than a theoretical possibility or a statistical annoyance, physics was in one of those especially fertile periods where the universe seemed determined to reveal new things faster than people could comfortably classify them. This was both exciting and deeply inconvenient, which is usually a sign that science is proceeding exactly as it should. The discovery of the lambda did not happen in the neat modern style where a large collaboration announces a result with polished plots, tidy significance estimates, and a press release that has been revised 17 times by committees who all fear adjectives. It happened in an earlier era of particle physics. When the tools were different, the evidence often came in photographs, and the subatomic world was being uncovered in a much more improvisational way. To understand how the lambda was first discovered, it helps to remember what physicists did and did not know at the time. They already knew about electrons and protons. Neutrons had been discovered. Nuclear physics was well underway. Cosmic rays had become an important source of high-energy phenomena, because before particle accelerators reached the energies needed to create many new particles reliably, nature was kind enough to run her own violent experiments in the upper atmosphere. High-energy particles from space would strike atoms in the atmosphere and produce showers of secondary particles. These in turn could be detected on the ground or in specially arranged experiments, and if one was patient enough, careful enough, and perhaps slightly tolerant of long hours staring at tracks in detector images, one could begin to notice that not everything appearing in those interactions belonged to the familiar cast of particles. This is where the story becomes wonderfully concrete. The early discovery of particles such as the lambda was not driven first by abstract equations, announcing their existence in a clean and triumphant way. It was driven by strange tracks, odd decay patterns, unusual events that left behind shapes in cloud chambers, nuclear emulsions, and later bubble chambers. The evidence looked visual before it looked conceptual. One saw traces, forks, bends, sudden appearances of particle paths where previously there had been none, and from those patterns one tried to reconstruct what invisible and short-lived object must have existed in the middle of it all. That style of physics required a kind of practical imagination. It was not enough to know theory. One had to look at the aftermath of events, and infer the unseen parent particles from the children they left behind. This is one of the reasons the discovery of strange particles is so historically interesting. It was detective work in a very literal sense. Something had happened. Something not directly visible had been there. It had left clues in the form of charged particles curving through magnetic fields, or appearing from a secondary point away from the primary interaction. The job of the physicist was to say, with as much confidence as possible, what hidden event could explain what the detector had recorded. The lambda first came into view through this sort of indirect evidence. It was not detected as a neat little isolated object sitting still and waiting to be introduced. It was reconstructed from its decay. That fact is essential. The lambda is unstable, and although by particle standards it lives long enough to travel a measurable distance when moving quickly, it does not last long enough to be treated as part of ordinary stable matter. So the first discovery of the lambda was really the discovery of a characteristic decay pattern, together with enough repeated evidence to conclude that a new neutral particle with a definite mass and lifetime must be responsible. One of the classic signatures associated with the lambda is that it decays into a proton and a pion, specifically a negatively charged pion in one common channel. What made this striking in early detectors was that the lambda itself was neutral, meaning it did not leave a visible charge track before the decay. Then, at some point away from the original interaction site, two charged tracks would suddenly appear, one identifiable as a proton and the other as a pion. This gave rise to a very distinctive shape. It looked as though a neutral invisible parent had travelled some distance and then split into two visible charged daughters. That secondary decay point, displaced from the primary production point, was one of the great clues. There is something deeply satisfying about that geometry. A charged particle draws a track because it interacts electromagnetically with the detector medium. A neutral particle often does not, at least not directly in the same visible way. So when a neutral unstable particle decays into charge products, you get a sort of delayed revelation. The parent remains unseen, but its existence is betrayed by the sudden birth of visible tracks away from the original collision. It is almost theatrical. The lambda does not appear on stage itself. It sends in two unmistakable witnesses instead. In the late 1940s and early 1950s, physicists studying cosmic rays began reporting such unusual events. Among the key moments was the identification of so-called V-shaped events in cloud chamber and photographic emulsion data. These were named quite straightforwardly because the charged decay products often formed a visible V-shape emerging from a point where no incoming charge track was seen. One does admire the economy of naming in such cases. Sometimes physics vocabulary becomes grand and baroque, and sometimes it simply says yes, that looks like a V, let us call it that and proceed to change the history of particle theory. These V events turned out to be associated with the decay of neutral strange particles, including the lambda and certain neutral mesons. Distinguishing among them required careful measurement of masses, momenta, and decay products. This was not trivial work. Experimentalists had to measure the curvature of charged tracks in magnetic fields, estimate particle momenta, identify which track belonged to which type of particle based on ionization or kinematic consistency, and then reconstruct the parent mass from the observed daughters. If enough events clustered around a particular mass value and showed a consistent pattern, that was strong evidence for a new particle species. The lambda emerged from exactly this sort of painstaking reconstruction. It was identified as a neutral particle heavier than the proton, decaying into a proton and a pion, with a lifetime longer than one would expect for a purely strong decay. That combination of features mattered enormously. It meant the lambda was not just another resonance disappearing almost instantly through the strong interaction. It had the characteristic delayed decay associated with the new class of strange particles. Its production in high-energy interactions suggested the strong interaction had helped create it. but its decay timescale suggested the weak interaction was responsible for its demise. This peculiar split between birth and death was one of the reasons the Lambda became so important so quickly. It is difficult to overstate how significant that was at the time. Remember, this was before the full quark model. Physicists were not yet saying with modern ease that the Lambda contains an up quark, a down quark, and a strange quark. Instead, they were building up the case that there existed a whole category of particles whose behaviour required new conceptual tools. The Lambda was one of the flagship examples. It gave a concrete case of a neutral baryon that was clearly not just a neutron by another name. It had the wrong mass, the wrong production context, the wrong lifetime, and the wrong decay pattern for that. Something new had been found. The role of cosmic rays in this story is especially charming because it reminds us that for a long time the universe itself supplied the highest energy particle beams available. Before giant machines took over that responsibility, physicists had to use what nature sent from space. Cosmic ray research was messy, opportunistic, and full of surprises. Detectors were placed at high altitudes, on mountains, in balloons, in underground laboratories. Every unusual event carried the potential to reveal something new. The Lambda was among the discoveries born from this era, when particle physics still felt partly like hunting, and partly like careful archaeology of invisible processes. Then, as accelerator technology improved, the study of the Lambda became much more systematic. Once physicists could produce high-energy collisions under controlled laboratory conditions rather than waiting for cosmic rays to cooperate, strange particles could be generated more reliably and studied in greater detail. This helped confirm and refine what had first been glimpsed in cosmic ray events. Accelerator experiments reproduced the Lambda and measured its properties more precisely. What had started as a puzzling visual signature became an established member of the particle catalogue. There is something rather lovely in that progression. First comes the odd photograph or track event, the isolated piece of evidence that does not quite fit existing categories. Then comes repeated observation, careful reconstruction, and the realization that a new particle is needed to explain what is being seen. Then comes classification, theory, and eventually a deeper constituent understanding. The Lambda followed that path almost perfectly. It moved from anomaly to specimen to structural clue. Early detectors deserve more appreciation than they often receive in simplified historical accounts. Cloud chambers, for example, were elegant devices in which charged particles passing through a supersaturated vapour left visible condensation trails. It sounds almost magical, and in a sense it was, though of course grounded in meticulous physics. Bubble chambers later performed a similar sort of visual service in a liquid medium, producing photographs filled with curling and branching tracks. Nuclear emulsions recorded tracks in photographic materials with very fine spatial resolution. These methods allowed physicists to see evidence of particles in a way that was at once deeply physical and strangely artistic. Some of the images from that era look like abstract drawings until one knows what they represent, and then suddenly every fork and curve becomes a sentence in the language of matter. The Lambda's discovery depended on learning to read that language. A neutral parent could not be followed directly, but the proton and pion from its decay could. Their momenta could be measured, their geometry could be reconstructed backward to a common origin point. The invariant mass of the pair could be inferred. Enough such events built up a persuasive picture. Here was a new neutral particle. Here was its characteristic decay. Here was its mass. Here was its lifetime scale. Physics often proceeds by accumulating such mutually reinforcing clues until the only sensible conclusion is that the particle is real. One should not imagine, though, that everyone immediately agreed on every detail with serene confidence. New particles in that era often came with disputes, competing interpretations, and the usual healthy amount of skepticism. This is normal. Scientific discovery is not a procession of people instantly nodding in perfect unison. It is a process of checking, doubting, recalculating, refining, and occasionally realizing that what one thought was a new object was actually an experimental misunderstanding or a different known process wearing an unusual hat. The Lambda survived that scrutiny. It kept appearing. Its properties remained consistent. It earned its place. The naming of the Lambda particle is another small but telling detail from the culture of the field. Greek letters became common labels for particles as the catalogue expanded, and Lambda was one among them. The modern designation often includes a zero because the ordinary lambda is electrically neutral. That naming style reflects the period when particle physics was rapidly growing its inventory and needed a system that was practical, memorable, and only occasionally intimidating to everyone else. By then the lambda was not just a curious event class, it was a named particle with a recognised place in the subatomic landscape. What made its discovery particularly valuable was not merely that it added one more item to the list. It helped reveal the existence of a whole new pattern in nature. The lambda's delayed decay and associated production helped motivate the concept of strangeness. Its properties fit the emerging scheme in which certain particles carried a new quantum number conserved in strong interactions but not in weak decays. Later, when the Quark model arrived, the lambda became one of the cleanest examples of a strange baryon, a 3-quark particle containing one strange quark. But all of that later theoretical clarity rested on the fact that experimentalists had first learned how to recognise the particle in the data. This interplay between experiment and theory is one of the great strengths of physics, and the lambda is an excellent case study. Theory did not simply summon the particle from nowhere. Experiment found something odd. Theory invented strangeness to organise the oddness. Later theory refined that organisation into the Quark model. More experiments then confirmed the deeper picture. At each stage, the lambda was both a fact and a clue. It existed as a measurable particle, and it pointed toward a wider structure still being uncovered. There is also a broader historical point here. The discovery of the lambda belongs to the era when particle physics shifted from the relatively spare world of early nuclear constituents into the much richer world of hadrons and internal symmetries. Before that expansion, it might still have seemed possible that matter's substructure would remain fairly simple. The lambda and its strange companions complicated that hope immediately. They announced that the proton and neutron were not the only baryonic possibilities. They hinted that new kinds of internal content were possible. They foreshadowed the eventual quark classification and the modern understanding of hadronic families. In that sense, the lambda was not merely discovered. It helped open the door to a new style of particle thinking, and it did so while being invisible at birth and known chiefly by its aftermath, which somehow feels appropriate. The lambda is a particle whose nature is inseparable from decay. Even its first appearance in science came through the traces left behind after it had already ceased to be itself. This is one of the reasons unstable particles are so intellectually rich. They force us to think in terms of processes rather than static objects. You do not learn the lambda by placing it on a shelf. You learn it by watching how it appears and how it vanishes. By the time the lambda became an established part of the particle catalogue, physicists had also begun to realise that the subatomic world obeyed an intricate system of conservation laws more subtle than the old simple categories allowed. Charge remained conserved, yes, but now strangeness seemed to matter too, at least in certain processes. Associated production became part of the story. Lifetimes became diagnostic. Decay channels became signatures. The lambda fit into all of this beautifully. Its discovery was one of the episodes that transformed particle physics from a field with a few familiar constituents into a much larger enterprise of classifying and explaining a whole hidden population of possible matter states. That is perhaps the real historical importance of how the lambda was discovered. It was not just that someone found a new particle, it was that the methods used to find it and the conceptual puzzles it raised became part of the foundation of modern particle physics. A neutral particle travelling invisibly, decaying into visible daughters, leaving a displaced vertex in a detector, being reconstructed from kinematics and repeated event patterns, That whole style of reasoning is still central to the field today. Modern detectors are vastly more sophisticated, of course, and the data are processed by computers, rather than examined only by human eyes over trays of photographs. But the logic remains the same. Something unseen is inferred from what it turns into. The Lambda helped teach physicists how to trust that logic. So the first discovery of the Lambda was both a specific event in the history of science and part of a much larger transition. It was born out of cosmic ray studies and early detector technologies. It emerged through V-shaped decay signatures and careful kinematic reconstruction. It challenged older expectations by living too long for a strong decay, and yet being produced as though the strong interaction were involved. It helped give rise to the concept of strangeness, and later it found its natural home in the quark model as a baryon built from up, down, and strange quarks. All of that matters because it leads directly into the next level of understanding. Once the Lambda had been discovered and recognized as a real strange baryon, physicists needed to understand not just that it existed, but what rules were governing its existence at all. Why were some particles allowed and others not? What kept quarks together inside baryons? What conservation laws had to be obeyed in production and decay? The discovery gave them the specimen. The next task was to understand the rules of the cage, if one may continue the zoo metaphor just a little longer, because inside that hidden population of particles it is the quiet rules, not merely the dramatic discoveries, that determine who can exist and for how long. Once the Lambda had been recognized as a real particle, and not merely an odd pattern in detector photographs, the next challenge was to understand why such a thing could exist at all. This is where particle physics becomes less like a catalogue and more like a legal system, though admittedly one enforced by the universe rather than by anyone filling out forms in triplicate. The subatomic world is not random. Particles do not simply appear because they feel like it, combine because they are lonely, or decay because their contracts have expired. They obey rules. Some of those rules are strict conservation laws, some are restrictions built into the fundamental interactions, some arise from the way quantum states are allowed to fit together, and all of them matter for the Lambda particle because the Lambda is not just a collection of three quarks. It is a collection that nature allows, holds together for a brief but definite time, and then transforms according to a very specific set of permissions. At first glance, one might think the basic question is simple. 3 quarks are in a baryon. Fine. What else is there to say? Quite a lot, as it happens, because quarks are not loose ingredients and baryons are not accidental clumps. The universe is choosy about what combinations are allowed. The Lambda exists only because several quiet rules are all satisfied at once. Its 3 quarks can be bound by the strong interaction. Their charges add up correctly. Their colour charges combine in the right way. Their quantum state respects the deeper requirements imposed by the kind of particles quarks are. Its total spin works out properly. Its existence does not violate the relevant conservation laws. All of that is happening beneath the surface of the simple sentence that says the Lambda is made of an up quark, a down quark, and a strange quark. Perhaps the most important of these quiet rules is the strong interaction itself, because without it there would be no baryons of any kind. The strong interaction is the force that binds quarks together into hadrons. It is not merely strong in the casual sense of being a bit more forceful than the others. At the distances relevant inside hadrons, it is the dominant interaction shaping the structure of protons, neutrons, lambdas, and all the rest. It is carried by particles called gluons, which is one of those names that sounds almost suspiciously friendly for something responsible for one of the most profound pieces of the universe's architecture. Gluons mediate the interaction between quarks, continuously exchanged inside the hadron, binding them into a composite whole. But the strong interaction is not a simple sticky substance. It is a full quantum field theory called quantum chromodynamics. The word chromodynamics includes the label colour, and this is where one of particle physics' most famous bits of confusing vocabulary enters the room. Quarks carry a type of charge called colour charge, but this has nothing to do with visual colour. No one is looking inside a proton and finding something tastefully blue beside something slightly crimson. Colour is just the name given to a kind of charge relevant to the strong interaction. Quarks come in 3 colour types, and gluons carry combinations associated with that colour structure. The crucial point is that observable hadrons must be colour neutral. Nature does not present us, under ordinary conditions, with free particles carrying exposed colour charge. The colours must combine into a neutral whole. That requirement alone explains a great deal about why baryons look the way they do. A baryon consists of 3 quarks, one of each colour in the simplified picture, combined so that the whole object is colourless in the physically observable sense. A meson, by contrast, uses a quark and an antiquark whose colour charges cancel one another. The lambda is a baryon, so its 3 quarks must satisfy that colour neutrality condition. This is not optional. It is one of the silent entry requirements for being an observable hadron at all. Without it, there is no stable or even temporarily stable colourless object for the outside world to detect, and already that tells us something interesting about the phrase, hold particles together. The strong interaction does not merely keep quarks from drifting apart inside a pre-existing particle. The pattern of allowed colour combinations is part of what defines the particle in the first place. The lambda is not a colourless box into which quarks are placed. The lambda is the colour-neutral bound state resulting from quarks interacting through quantum chromodynamics. The rules are structural, not decorative. There is another remarkable feature of the strong interaction that deepens this further. Quarks are confined. That means that under ordinary conditions they do not appear in isolation. If one tries to separate quarks, the energy stored in the strong field grows, rather than falling away gently, as happens with some other forces over distance. This makes the isolation of a single quark extraordinarily difficult in a way that ordinary intuition does not anticipate. Instead of politely letting you pull a quark free and examine it like a bead lifted from a necklace, the energy involved tends to create new quark-antiquark pairs, leaving you again with colour-neutral hadrons rather than solitary quarks. Nature, in effect, refuses to leave colour exposed. The lambda exists because quarks are allowed to bind together in a colour-neutral 3-quark configuration, and that same underlying physics is why you never meet its constituent quarks separately in the detector afterward. This confinement is one of the quiet rules that gives hadrons their peculiar dignity. They are not merely probable gatherings. They are the observable form quark matter takes under these conditions. The lambda, therefore, is held together not just by some generic attractive force, but by the detailed machinery of confinement and colour neutrality, operating within quantum chromodynamics. That is one layer of order. Another layer involves electric charge. This sounds almost too obvious to mention, but it matters because charge conservation is one of the most robust laws in physics. The lambda is electrically neutral because the charges of its quarks add up to 0. The up quark carries a positive fractional charge. The down quark and the strange quark each carry a negative fractional charge of smaller magnitude. Together they sum to neutrality. This is not merely a bookkeeping convenience. Electric charge affects how particles interact electromagnetically, how they curve in magnetic fields, how they show up in detectors, and which decay products are possible. A neutral baryon behaves differently from a charged one, and the lambda's neutrality is part of the reason its discovery involved indirect reconstruction from charged decay products rather than a visible incoming track of the parent itself. Then there is baryon number, another conserved quantum number that quietly shapes what particles are allowed to be. Quarks carry baryon number in such a way that 3 quarks together make a baryon with baryon number 1. An antiquark carries the corresponding opposite amount. This is part of the general conservation scheme that keeps particle processes orderly. When a lambda is created, baryon number is conserved. When it decays, baryon number is conserved. That is why the lambda can decay into a proton and a pion without any violation of baryon number. The proton is a baryon, the pion is not, and the total baryon number before and after matches correctly. This may sound like administrative detail, but it is exactly these administrative details that make particle physics possible. Without them, predictions would dissolve into guesswork. Spin is another of the quiet rules, or more precisely one of the quiet properties that must fit into the overall allowed quantum structure. The lambda has half-integer spin, like the proton and neutron. Quarks themselves are fermions, particles that obey the rules associated with half-integer spin and are subject to the Pauli exclusion principle in the appropriate contexts. Now, this is where the internal architecture of baryons becomes especially subtle, because when you have three quarks in a hadron, their total wave function must satisfy symmetry requirements. The different parts of the quantum state, spatial, spin, flavor, and color, all combine in ways that must respect the fundamental identity of quarks as fermions. This is one of those areas where the deep mathematics becomes formidable rather quickly, but the core physical idea can be stated simply enough. Nature does not allow arbitrary quantum arrangements. If the quarks are of certain types and in certain relative states, the total quantum description must have the right symmetry properties under exchange. In baryons, the color part of the wave function plays an especially important role in making the whole thing possible. It is arranged in a way that allows the rest of the quantum state to satisfy the required overall fermionic behavior. This may sound abstract, but it is part of the reason that the hadron spectrum has the patterns it does. The lambda is not simply three named quarks in a sack, it is a very specific allowed quantum arrangement of those quarks. This is also why not every imaginable three-quark combination produces a stable or distinct observable baryon in the same way. The internal state has to work, spin coupling has to work, color structure has to work, flavor content matters. The strong interaction allows many combinations, but only certain structured states emerge as recognized hadrons. The lambda is one of them because its quark content and quantum numbers fit into an allowed and definite configuration. Flavor, of course, is a key part of the story here. Up, down, and strange are flavors of quark, and the lambda contains one of each. This gives it a particular flavor structure that distinguishes it from the proton and neutron. But flavor is not merely a label attached after the fact. It affects mass, decay possibilities, and the role of different interactions. The strong interaction does not change quark flavor. That is an extremely important quiet rule. It means that while the strong interaction can bind the up, down, and strange quarks together into the lambda, it cannot on its own turn the strange quark into an up or down quark later. Flavor changing of that sort requires the weak interaction, so the same set of rules that holds the lambda together also explains why it does not immediately dissolve through the strong interaction into non-strange particles. The strong interaction preserves the strange quark's identity while binding it into the baryon. That point is worth lingering over, because it often confuses people at first. If the strong interaction is so strong, why does it not simply rearrange everything into the lightest possible configuration instantly? The answer is that the strength of an interaction is not the same thing as permission to violate every quantum number in sight. The strong interaction is powerful, but it is rule-bound. It conserves flavor in this context. It conserves strangeness in the sense relevant to hadronic processes. So once a strange quark is present in the lambda, the strong interaction cannot make it disappear into a lighter non-strange particle all by itself. The lambda remains a valid hadron. Only later, through the weak interaction, can the strange quark change flavor and open the route to decay. This is one of the most beautiful examples in particle physics of strength and constraint existing together. The strongest force involved is not the one that gets the final say over the particle's identity. Strangeness itself, historically introduced before the quark model, is another quiet rule in the sense that it governed how these particles appeared and disappeared in experiments. In the modern picture, strangeness is tied to the presence of strange quarks. Strong interactions conserve it. Weak interactions can change it. This explains why strange particles such as the lambda were often produced in associated pairs or with balancing strange content in strong collisions. The net strangeness had to come out right. It also explains why their decays were slower than typical strong decays. Their strangeness had to be removed by the weak interaction. So the lambda sits in a beautifully disciplined space between these rules. It is born under one set of emissions and dies under another. Energy and momentum conservation also quietly oversee everything. A lambda cannot simply decay into anything one might find narratively appealing. The final particles must together carry the right total energy and momentum, and their combined mass energy must fit what was available from the parent. This is why the lambda decays into particular lighter products rather than arbitrary, fantastical outcomes. In every allowed decay, the numbers must balance. These conservation laws are so fundamental that physicists often speak of them with the calm confidence usually reserved for sunrise and tax forms. They are not suggestions. They are the framework within which all allowed processes occur. The same goes for angular momentum conservation. Because the lambda has a definite spin, the total angular momentum of the decay products must match appropriately. Again, this shapes what decays are allowed and how the products emerge. When experimentalists study lambda decays, they are not just counting events. They're also learning about the angular distributions and correlations among the decay products, because those reveal how the underlying rules are being obeyed. The quiet rules are not silent because they are unimportant. They are silent because they operate everywhere, all the time, without announcing themselves. Another subtle but crucial point is that the mass of the lambda is not merely the sum of 3 quark masses written on a label. In hadrons, much of the total mass comes from the energy stored in the strong interaction and the motion of the quarks and gluons inside. This is one of the most extraordinary facts about ordinary matter as well. The proton's mass is not mostly the simple sum of its quark masses. It arises largely from the dynamics of the strong interaction. The lambda follows the same general principle, though with the strange quark contributing more than an up or down quark would. This means the quiet rules that hold the lambda together are also the quiet rules that generate much of what the particle is, including its mass. The strong interaction is not just the glue. It is a major source of the physical substance of the hadron. If one steps back a little, a pattern begins to emerge. The lambda exists because several kinds of order overlap. There is gauge structure in the strong interaction, color neutrality, confinement, conservation of electric charge, conservation of baryon number, spin and wave function symmetry requirements, flavor rules, and the broader conservation of energy, momentum, and angular momentum. None of these by itself explains the whole particle. Together they make the lambda possible. They do not merely stop it from doing silly things, they define what it means for the lambda to be a lawful particle in the first place. This is why particle physics often feels less like studying tiny objects, and more like studying allowed forms in a tightly governed language. The lambda is a valid sentence in that language. Its grammar is strict, its vocabulary is limited, its punctuation can be lethal if one makes an error. But when all the rules are satisfied, the sentence exists. Then later, through the weak interaction, it is rewritten. There is also something unexpectedly reassuring in how little of this is improvised. The subatomic world is not a noisy accident at the bottom of the matter. It is disciplined. Even the instability of the lambda is disciplined. It is held together strongly while it exists. It carries the right quantum numbers. It cannot decay just any way it likes. It cannot shed its strange quark through the strong interaction. It must wait for the weak interaction to do the necessary flavor-changing work. Its lifetime, therefore, reflects not only that it is unstable, but why it is unstable in the very particular way it is. The quiet rules shape the whole narrative from formation to decay. One could almost say that the lambda is an agreement among several forces and principles. The strong interaction agrees to bind the quarks. Color neutrality agrees to allow the bound state to exist as an observable hadron. The conservation laws agree that nothing improper has been attempted. The flavor structure agrees that this is a strange baryon and therefore not ordinary stable matter. And the weak interaction waits patiently in the background with the paperwork for the eventual transition. It is perhaps not the most glamorous picture, but it is accurate in spirit. The lambda is lawful all the way through. This becomes especially important when comparing the lambda with more familiar particles. A proton is held together by the same basic strong interaction, obeys the same core conservation laws, and is also a baryon. So what makes the lambda different is not a completely new set of rules, but a different use of the same rules because of its strange quark content. In that sense, the lambda is a wonderfully instructive particle. It shows us continuity and difference at once. It belongs to the same world as the proton and neutron, yet it reminds us that changing one ingredient inside a tightly governed system can alter mass, lifetime, and decay behavior dramatically. That is often how physics progresses. One studies a familiar case until it feels almost comfortable. Then one shifts one parameter, swaps one ingredient, changes one quantum number, and suddenly the deeper architecture becomes visible. The lambda does exactly that. It is close enough to the proton and neutron for the comparison to be meaningful, and different enough for the comparison to be revealing. It exposes the quiet rules by forcing us to notice them, and those rules matter even more once we turn directly to the central mystery that has been waiting in the background all along. The strong interaction can hold the lambda together, the conservation laws can bless its existence, and the quantum structure can make it a real baryon. Yet despite all of that, the lambda does not last. It is lawful, but temporary. The reason lies not in a failure of those rules, but in their coexistence with another interaction entirely, one that can do what the strong interaction cannot. That is where the real question begins to sharpen, because once the lambda's internal order is understood, the next thing one wants to know is why this perfectly legitimate particle is still so unstable. The most interesting thing about the lambda particle is that nothing about its existence is sloppy, accidental, or half-formed, and yet it still does not stay what it is for very long. That is really the heart of the matter. The lambda is not unstable because it is a badly assembled particle. It is not held together weakly in the ordinary sense. It is not some failed baryon that almost qualifies as real and then falls apart from embarrassment. Quite the opposite. It is a genuine hadron, a perfectly valid 3-quark bound state, held together by the strong interaction in exactly the lawful way baryons are supposed to be held together, and still it decays. That combination of solidity and impermanence is what makes the lambda so scientifically useful. It exists long enough to be identified, but not long enough to become ordinary. So the question is not whether it is real. The question is why something so real disappears so quickly. The short answer, though we will not stop there, is that the lambda is unstable because one of its 3 quarks is a strange quark, and strange quarks can change into lighter quarks through the weak interaction. That is the central fact. Everything else grows from it. The lambda is made of 1 up quark, 1 down quark, and 1 strange quark. The strong interaction binds those 3 together into a baryon. But the strong interaction does not change quark flavor. It cannot take the strange quark and turn it into an up or down quark. The weak interaction can. Once that flavor change becomes possible, the lambda has a route to transform into lighter particles, and because lighter final states are available, the lambda does not remain what it is forever. This is one of those cases where the word unstable can mislead people if they bring too much everyday intuition with them. In daily life, something unstable is often something poorly balanced or weakly supported. A stack of books leaning at a bad angle is unstable. A ladder placed on a loose stone is unstable. A bad chair at a wedding venue is unstable, in a way that can turn a pleasant evening into a story told for years. But the lambda's instability is not that kind. It is not wobbling on the verge of collapse because the strong interaction is failing to bind its quarks properly. The strong interaction is doing its job extremely well. If the weak interaction did not exist, or if flavour-changing weak decays were not allowed, the lambda would simply remain a strange baryon. The instability comes not from weak binding, but from the existence of an alternate permitted future. That future matters because physics is full of systems that move toward lower energy configurations when a lawful path is available. At the particle level, this often means that a heavier particle can decay into lighter particles if all the relevant conservation laws are respected, and if an interaction exists that can mediate the transformation. The lambda is heavier than the proton, and heavier than the combination of particles into which it can commonly decay. That means there is room, energetically speaking, for the lambda to become something lighter while preserving the necessary conserved quantities. Nature is not obliged to keep the heavier arrangement intact if there is a lawful and available way to turn it into a lighter one. This is where the strange quark becomes decisive. The lambda owes its identity to the strange quark, but it also owes its impermanence to it. Strange quarks are heavier than up and down quarks. Because of that, a baryon containing a strange quark carries extra mass compared with one made only of up and down quarks in a similar overall class. That extra mass is part of why lighter final states are available, but more importantly, the strange quark can be changed by the weak interaction into an up quark or a down quark. Once that happens, the whole baryon is no longer the same particle, its internal recipe has changed, and because the weak interaction is allowed to do exactly that sort of flavour-changing work, the lambda comes with a built-in exit route. If one wants a somewhat plain and reliable way to think about it, the lambda is like a stable house built on land that the universe has legally zoned for redevelopment. The house is real. It is not badly built. It can stand there perfectly well, but the paperwork already allows another arrangement that uses the same resources more economically, and eventually the transition goes through. That is not a perfect analogy, of course, because quarks are not bricks, and the weak interaction is not a municipal office, though some bureaucracies do produce effects that appear only after a mysterious delay. Still, the point stands. The lambda is not unstable because it fails to exist properly. It is unstable because its particular existence is not the lightest lawful arrangement available once the weak interaction is allowed to act. The weak interaction deserves careful attention here because it differs from the strong interaction in exactly the way the lambda story requires. The strong interaction binds quarks into hadrons and preserves quark flavour in the relevant processes. It is extremely powerful and extremely fast. If the lambda could decay into lighter products through the strong interaction while changing nothing forbidden, it would do so on a much shorter timescale. But that route is closed because the lambda's strangeness cannot simply vanish under the strong interaction. The strange quark remains strange so long as only the strong interaction is involved. Therefore, the lambda cannot use the strongest available force to rid itself of strangeness and become a lighter, non-strange baryon. That is why the weak interaction takes over the story. The weak interaction is uniquely suited to changing quark flavour. It can convert a strange quark into an up or down type through processes involving the charged weak bosons. In the case of the lambda, that means the strange quark can transform into a lighter quark, and in the course of that transformation, the baryon can decay into a proton and a pion, or into a neutron and a neutral pion, among other possibilities. Those are lighter configurations. They conserve the required quantities. They are allowed. The lambda, therefore, has a pathway out of its original identity. Now, one of the subtler and more beautiful features of the lambda's instability is that it is not as unstable as it might be if the strong interaction were responsible for its decay. This was historically one of the clues that the lambda belonged to the strange particle family in the first place. Strong decays are very fast by particle standards. Electromagnetic decays are generally slower than strong ones, but still faster than weak decays in many relevant cases. Weak decays are comparatively slow. The lambda lives long enough for experimentalists to reconstruct a measurable displacement between the point where it was produced and the point where it decayed. This is not because the lambda is nearly stable in any ordinary human sense. It is because the weak interaction is much less intense than the strong one, and therefore gives the lambda a lifetime that is short, but not vanishingly short by subatomic standards. This duality is the crucial thing to appreciate. The same particle is held together by the strong interaction while it exists and then transformed by the weak interaction when it decays. There is no contradiction in that. Different interactions are responsible for different aspects of its behaviour. One gives it existence as a hadron, the other gives it an eventual way out. So when physicists say the lambda is unstable, they are really describing the outcome of a competition, not between binding and not binding, but between remaining a strange baryon and using the weak interaction to become something lighter and more ordinary. Another way to frame this is to say that the lambda is metastable rather than fragile. Metastable systems are real states that persist for a while, even though a lower energy state is available, because the transition requires a specific mechanism or pathway. That is a very useful concept across physics. A system can be perfectly genuine and still not be final. The lambda is a hadronic example of exactly that. It is not the lowest mass baryon with the same baryon number and electric neutrality available to nature, because once strangeness is removed, lower mass possibilities exist. But the removal of strangeness requires the weak interaction. So the lambda waits, in a statistical sense, for that weak decay to occur. This statistical aspect matters too. Individual lambda particles do not carry tiny countdown clocks with identical alarm times. Quantum decay is probabilistic. One lambda may decay a little sooner, another a little later, but across many lambdas one observes a characteristic lifetime. That lifetime is one of the particle's defining properties. It reflects the probability per unit time that the weak decay process will happen. So instability here does not mean uncertainty in the vague everyday sense. It means a definite statistical law governing a transformation. The lambda is unstable with precision. The available decay products also help explain why the lambda does not stay around. One of its common decay modes produces a proton and a negatively charged pion. Another common mode produces a neutron and a neutral pion. These outcomes are lighter than the original lambda and satisfy the conservation rules. Charge is conserved, baryon number is conserved, energy and momentum are conserved, angular momentum is conserved. What changes is the flavour content, because the strange quark in the original lambda becomes a lighter quark via the weak interaction. That flavour change is the essential event. Once it has happened, the original strange baryon is gone. There is something almost instructive in how economical the universe is here. The lambda contains one unusual ingredient relative to ordinary baryons, the strange quark, and that one ingredient is exactly what gives the particle both its interesting identity and its built-in route to decay. The lambda is heavier because of the strange quark. It is strange because of the strange quark. It cannot decay strongly into ordinary matter because of the flavour-preserving nature of the strong interaction. It can decay weakly into ordinary matter because the weak interaction can change the strange quark. One ingredient changes everything. That is a very common pattern in physics. Alter one deep variable, and the whole phenomenology shifts with it. It is also worth noticing what does not make the lambda unstable. It is not unstable because baryons in general are unstable. The proton appears stable on all observed timescales. The neutron, while unstable as a free particle, becomes stable inside many nuclei. So baryonhood itself is not the issue, nor is neutral charge the issue, because electrical neutrality does not imply instability. The neutron is neutral and still has a very different story from the lambda. The crucial distinguishing feature is the lambda's strange quark content, combined with the availability of weak decay into lighter, non-strange final states. And perhaps this is the moment to emphasize the remarkable specificity of the standard model. The lambda is not unstable by a hand-waving principle that exotic particles simply do not last. It is unstable for exact reasons tied to quark masses, interaction types, conservation laws, and coupling strengths. The Standard Model explains not only that strange baryons can exist, but also why they tend not to be permanent, which interactions create them, which interactions destroy them, and roughly how long they survive. That is an extraordinary amount of order hidden beneath what at first sounds like a simple statement about a short-lived particle. The quark mixing structure of the weak interaction also plays a role in the quantitative details. Quarks do not all change into one another with equal ease. The weak interaction has a pattern of couplings among flavors, encoded in what physicists call the quark mixing matrix. The strange quarks transitions to lighter quarks occur with particular strengths, and those strengths influence decay rates. We need not wander too far into the mathematical forest here, especially since you asked for everything to remain verbal, but it is important to say that the lambda's lifetime is not just a generic result of weak decay. It depends on how the weak interaction couples the strange quark to the lighter flavors and on the detailed hadronic structure of the initial and final states. In other words, even the speed of the lambda's instability is law-governed down to a rather impressive level of detail. There is also a historical irony here that is too good to ignore. The lambda was once called strange because its behaviour seemed strange before the relevant theory had settled into place. It was produced promptly, suggesting one kind of interaction, and decayed more slowly, suggesting another. That split behaviour looked odd enough to motivate the concept of strangeness as a conserved quantity in strong production but not in weak decay. Later, with the quark model, the strangeness stopped being mysterious in the old sense. The particle was unstable for exactly the reason it had seemed strange in the first place. What had looked like peculiar behaviour turned out to be a clean consequence of deep rules. In that sense, the lambda is a very educational particle, because it teaches two lessons at once. First, the subatomic world often becomes intelligible only when one distinguishes carefully between the different interactions. It is not enough to know that forces exist. One must know which force is responsible for which stage of a particle's life. Second, instability is not the opposite of structure. The lambda is highly structured. Its decay does not undermine that structure. It reveals it. The very fact that the lambda decays through the weak interaction rather than the strong one is evidence about its internal content and the rules governing flavor change. One can push this a bit further. The lambda's instability is one of the reasons it became so useful experimentally. Because it lives long enough to travel a short but measurable distance before decaying, detectors can reconstruct secondary vertices, those displaced decay points that act as signatures of short-lived particles. If the lambda decayed immediately at the production point through the strong interaction, it would be far harder to isolate in the same way. If it were completely stable, it would be a very different sort of object and would change the composition of ordinary matter. Instead, it occupies a scientifically ideal middle ground. It is unstable enough to be interesting and stable enough to be identifiable. That balance is a gift to experimental physics, though I suspect the lambda itself would not take credit. There is a broader philosophical point lurking here as well. In ordinary life, we often imagine permanence as a mark of reality, and transience as a mark of lesser importance. Particle physics repeatedly overturns that instinct. Short-lived particles can be every bit as real and every bit as informative as stable ones. The lambda is unstable not because it is somehow less authentic than the proton, but because the universe contains more than one lawful arrangement for its ingredients and permits a transition from the heavier one to lighter ones. Reality, at this scale, is not a hierarchy of worthy lasting things versus flimsy temporary ones. It is a web of allowed states, some enduring, some brief, each revealing something about the rules beneath them. The lambda's instability also reminds us that particles are not little indivisible pebbles in the old classical sense. They are states in a quantum field theoretic world, and many such states are resonant or metastable rather than eternal. Their identity includes their decay channels and lifetimes. To ask why the lambda is unstable is therefore to ask why its place in the spectrum of allowed hadrons comes with an open weak decay route. The answer lies in the strange quark and in the weak interaction's special talent for changing flavour. That is the core of it. So the lambda particle is so unstable, not because it is weakly bound, not because baryons are generally flimsy, and not because the universe is being whimsical. It is unstable because it contains a strange quark, because strange quarks can transform into lighter quarks through the weak interaction, because the resulting non-strange final states are lighter and allowed, and because the strong interaction that binds the particle cannot itself remove the strangeness. The lambda therefore exists as a genuine hadron for a short statistical lifetime, and then decays along the weakly permitted routes into lighter particles. Its instability is exact, meaningful, and deeply tied to the structure of the Standard Model. Once one sees that clearly, the next natural step is not merely to say that the lambda decays, but to follow what actually happens when it does. Because the real drama of an unstable particle is never in the word unstable by itself. It is in the transformation, the products that appear, the routes nature chooses most often, and the signatures those decays leave behind for physicists to read. Once the lambda particle has been created and has spent its very short existence being exactly what it is, a neutral baryon made of one up quark, one down quark, and one strange quark, the next thing that happens is not a vague disappearance, but a very specific transformation. This is the important thing to keep hold of. Particles do not usually vanish in the theatrical sense of being there one moment, and then simply absent the next as if the universe had misplaced them. When a particle decays, what actually happens is that its energy, momentum, and quantum numbers are redistributed into other particles in a way that obeys the rules of physics. The lambda does not fade into nothing. It changes into something else, and the details of that change are exactly what make it so useful to study. The most common and most historically important thing that happens when a lambda particle decays is that it turns into a proton and a negatively charged pion, or into a neutron and a neutral pion. Those are the best known channels. In plain terms, the original strange baryon becomes a more familiar baryon together with a lighter meson. That is the broad picture. But hidden inside that apparently simple sentence is a very rich process involving the weak interaction, a change in quark flavour, a reshuffling of the particle's internal structure, and the release of the right amount of energy into the final products. Let us begin with the common decay into a proton and a negatively charged pion, because it gives the clearest illustration of what is going on. The lambda starts as an up quark, a down quark, and a strange quark bound together. During the decay, the strange quark is transformed by the weak interaction into an up quark. Once that happens, the composition of the baryonic part of the system is no longer the same as it was before. The remaining quark arrangement can settle into the form of a proton, which is made of two up quarks and one down quark. The process also produces the ingredients needed for the pion, so that the total final state becomes one proton and one negatively charged pion. The details are governed by the weak interaction, but the result is surprisingly neat. One strange baryon goes in, one ordinary baryon and one pion come out. This is one of the reasons the lambda is such a nice teaching example in particle physics. Its decay products are not impossibly exotic. They are things that fit naturally into the broader particle family picture. The proton is the familiar positively charged baryon at the heart of the hydrogen nucleus, and, by extension, at the heart of much of ordinary matter. The pion is one of the light mesons, central to the history of nuclear force theory and common in many hadronic processes. So when the lambda decays, it does not leave behind bizarre debris that belongs to some isolated subatomic side alley. It decays into particles that are well understood, and that connect directly to the rest of hadronic physics. The other important decay channel produces a neutron and a neutral pion. Here again, the broad logic is the same. The strange quark is changed by the weak interaction into a lighter quark, and the final arrangement becomes a neutron plus a pion instead of a proton plus a pion. The neutron, although unstable when free on long enough timescales, is still a much more ordinary and familiar baryon than the lambda. So in both of these common decays, the lambda moves from a strange baryon to a non-strange baryon, and in doing so, it sheds the strangeness that had defined its identity. This shedding of strangeness is the deepest thing happening in the decay. The lambda is not merely breaking apart, it is changing category. While it exists, it belongs to the class of strange baryons, because one of its quarks is strange. After the decay, the final baryon no longer contains that strange quark. The strange quark has changed flavour through the weak interaction, and with that one change, the entire nature of the particle is shifted. The lambda ceases to be itself because its defining constituent content has been altered. In this sense, decay is identity change at the most basic level. The particle is not rearranged cosmetically, its very quark-level definition is replaced. Now, because the lambda is neutral, and because its common decay products are charged in one of the main channels, the decay leaves a particularly useful experimental signature. The lambda itself does not leave a visible charged track before it decays, at least not in the way a charged particle would in the relevant detectors. But when it turns into a proton and a negatively charged pion, those daughter particles are charged and do leave tracks. So what an experimentalist often sees is not the lambda directly, but two charged tracks suddenly appearing from a point some small distance away from the original collision. That displaced point is the decay vertex, and it is one of the great clues that a short-lived neutral particle existed in between. There is something wonderfully disciplined about this. The lambda lives briefly, moves a little if it has enough momentum, and then the universe allows the weak decay to happen. Out come the daughter particles, each carrying a share of the original momentum and energy. The proton and pion then continue through the detector, curving in magnetic fields according to their charges and momenta. From those tracks, physicists work backward. They reconstruct the decay point, calculate the momenta, infer the parent mass, and conclude that a lambda must have been present. So when a lambda decays, it is not merely an event in microscopic reality. It is also the beginning of a chain of evidence by which that microscopic event becomes knowable. The word decay itself can be slightly misleading for another reason. In ordinary language, decay sounds gradual. Fruit decays slowly. Paper decays over time. Buildings decay with admirable patience and usually terrible maintenance budgets. Particle decay is not like that. The lambda does not slowly lose pieces over a long interval. It remains a lambda until the moment it decays, and then it is not a lambda anymore. The process is discrete. Before the decay, the original particle exists. After the decay, the daughter particles exist. The change happens in a single quantum event. That probabilistic waiting, followed by sudden transformation, is very unlike the continuous decay familiar from ordinary life, and it is worth keeping in mind because it makes the subatomic world feel at once stranger and more exact. What happens to the mass of the lambda during the decay is also important. The lambda is more massive than the sum of the final particle's rest masses in its common decay channels. That excess does not vanish. It is converted into kinetic energy of the daughter particles. In other words, the proton and pion come flying out with motion that reflects the energy released in the transformation. This is one of the reasons particle decays can be measured so carefully. The energies and momenta of the daughters contain information about the mass and identity of the parent. The lambda's greater mass compared with its final products is what makes the decay energetically possible, and the released energy becomes part of the daughter's motion. One must also remember that the decay must obey all the conservation laws that governed the lambda's life in the first place. Electric charge is conserved, baryon number is conserved, energy and momentum are conserved, angular momentum is conserved. The weak interaction can change flavour, but it does not simply suspend the rest of the universe's accounting procedures for convenience. everything still has to balance. That is why the final states are specific. They are not random outcomes chosen for dramatic effect. They are the results that satisfy the rules. Consider the common decay to a proton and a negatively charged pion. The lambda is neutral overall. The proton is positively charged. The negatively charged pion balances that, giving 0 total charge after the decay, just as before. Baryon number is 1 before the decay because the lambda is a baryon. After the decay, the proton carries baryon number 1 and the pion carries 0, so the total remains 1. Energy and momentum are carried away by the proton and pion together. Angular momentum works out consistently with the spin structure of the initial and final states. The strangeness changes because the weak interaction allows that to happen. The rest of the books remain clean. The probabilistic nature of the decay also deserves its own moment. If one creates many lambda particles under similar conditions, they will not all decay after exactly the same time. That is not how quantum decay works. Instead, there is a characteristic lifetime, meaning a statistical tendency. Some lambdas decay sooner, some later. But the overall distribution follows a precise law. This is why physicists speak of the lambda's lifetime as a definite quantity, even though no individual lambda carries a fixed appointment card for the moment of its end. The decay is random in the event-by-event sense, but highly predictable in aggregate. This blend of chance and law is one of the deepest and most persistent features of quantum physics. Now, beyond the main two-body decay channels, the lambda can in principle participate in other less common processes as well, including semi-leptonic decays where leptons appear among the products. These are less dominant but very important for probing the weak interaction in more detail. In such cases, the final state might include a proton together with an electron and an antineutrino, or a neutron together with an electron and an antineutrino, depending on the particular process. These channels are rarer, but they are extremely valuable because leptons interact differently from hadrons, and the decay distributions can reveal subtle features of the weak interaction and the internal structure of the lambda. Still, for the basic story, the dominant hadronic decays into a nucleon and a pion are what matter most. They are the simplest picture, and historically the most important in identifying the lambda. They also make clear what the decay accomplishes. The lambda stops being a strange baryon and becomes an ordinary baryon plus a meson. In doing so, it reduces the strange content of the final state to 0. That is the physical meaning of the decay. The strange quark does not survive as strange in the final hadronic identity. It has been transformed away. There is another subtle point here that often goes unnoticed but is rather lovely once seen. The lambda's decay is not merely a matter of particles leaving each other. It is the weak interaction acting inside a strongly bound hadron. That means the process is both local and deeply composite. One of the constituent quarks changes flavour, but because the quarks are bound in a hadron, the decay has to be understood in terms of the whole hadronic state before and after. In other words, the lambda is not just a box containing 3 quarks, one of which privately decides to resign. The internal change affects the whole composite system. The final proton or neutron is a new hadron, not just the leftover shell of the old one. This makes the decay a rich theoretical problem as well as an experimental one, because one is dealing not only with the elementary weak transition of a quark, but also with the strongly interacting environment in which it occurs. That environment matters because hadrons are not static collections. The quarks inside them are part of a dynamic quantum state with gluons and fluctuating C-quark contributions as well. So when the lambda decays, the simple quark-line picture is useful but not complete. The actual hadronic process reflects the full quantum structure of the bound state. That is one reason precision calculations of hadron decays can be demanding. The weak interaction may be responsible for the flavour change, but the strong interaction still determines the structure of the initial and final hadrons. The decay is therefore a meeting point between 2 fundamental interactions, one causing the transformation and the other defining the particles being transformed. One of the more fascinating aspects of lambda decay is that it also exhibits parity violation, because the weak interaction violates parity symmetry. This means the decay is not completely indifferent to left and right in the way the strong interaction would be. In practice, the angular distribution of the decay products can carry information about this asymmetry, especially if the lambda is polarized. This was a major subject of study in particle physics because weak decays provided one of the clearest windows into the fact that nature, at the level of the weak interaction, is not perfectly mirror symmetric. So when a lambda decays, the event is doing more than turning one particle into two or more. It is also offering a glimpse into one of the most surprising symmetry violations in modern physics. From the experimental point of view, what happens after the decay is also crucial. The daughter particles continue on their own path through the detector. The proton, being charged and relatively massive, leaves a track with specific curvature and ionization characteristics. The pion, being lighter and also charged in the main channel, leaves its own track. By measuring these, physicists can reconstruct the invariant mass of the parent. If the reconstructed mass repeatedly lands at the known lambda value, one has compelling evidence that the parent particle was indeed a lambda. So in practice, the decay is the beginning of the lambda's detectability. Before the decay, the neutral parent may remain hidden. After the decay, the evidence blooms outward. This is one of the reasons particle decays are so central to experimental physics. Unstable particles tell on themselves. They reveal their existence through what they become. In some cases, the daughters are easier to detect than the parent, and the lambda is a very good example. The displaced decay vertex and the identifiable proton and pion tracks make the lambda one of the classic reconstructible strange hadrons. In modern collider experiments, lambdas are still reconstructed this way, and studying their production and decay helps physicists understand not only the particle itself, but also the hadronization processes that create baryons out of energetic quarks and gluons. There is also a broader lesson in all this. What happens when a lambda particle decays is, in miniature, what happens throughout the unstable particle world. A composite state exists. A lower energy allowed state is available. A particular interaction provides the transition mechanism. Conservation laws shape the permitted final products. The decay occurs probabilistically but with a definite characteristic rate. The daughters carry away the evidence. In the lambda's case, all of this is especially transparent because the particle is simple enough to describe clearly and rich enough to connect to deep themes like flavor change, weak decay, hadronic structure, and parity violation. So when a lambda particle decays, it does not simply stop. Its strange quark is transformed by the weak interaction into a lighter quark. The original strange baryon identity is lost. A proton and a negatively charged pion often emerge, or a neutron and a neutral pion, carrying away the energy, momentum, and lawful consequences of the transformation. The event happens suddenly after a probabilistic wait. The daughter particles leave tracks. The decay point appears displaced from the production point, and from those traces physicists reconstruct the entire story backward, concluding that for one brief moment a lambda particle had been there at all. That naturally leads to the next question, because once one sees how the lambda reveals itself only through the aftermath of its decay, the real practical challenge becomes obvious. If the particle is neutral, short-lived, and known mostly by the tracks of its daughters, then how do scientists actually detect something so fleeting with confidence, precision, and enough repetition to turn single events into solid knowledge? By the time one understands what the lambda particle is and what happens when it decays, a very practical question begins to press in from the edges. How exactly do scientists detect something that does not last, does not usually leave a direct visible track before it decays, and exists on a timescale so short that any ordinary intuition about observation becomes almost useless? This is where particle physics becomes especially impressive, because it asks us to accept a rather counterintuitive idea. You do not always detect a thing by seeing the thing itself. Sometimes you detect it by seeing what it must have done, what it must have become, and the particular shape of evidence it leaves behind as it exits the scene. That style of reasoning is not unique to particle physics, but particle physics uses it with extraordinary discipline. If you hear thunder, you infer lightning whether or not you saw the flash. If you wake to a wet pavement and heavy clouds, you infer rain even if you slept through it. If a biscuit has vanished from the tin, and there are crumbs suspiciously close to someone's keyboard, one may begin forming hypotheses. In all these cases, the object or event of interest is not being observed directly at the moment of concern. It is being reconstructed from consequences. Particle physics does this too, but with much greater care, and with instruments designed to read consequences at a level far beyond the reach of unaided senses. The Lambda particle is an excellent example because it sits in exactly the awkward middle ground that forces experimental cleverness. If it were stable and electrically charged, one might simply track it through a detector more directly. If it decayed almost instantly through the strongest possible route, it might leave too little separation from the original interaction point to isolate easily. Instead, the lambda is neutral and short-lived, but not so short-lived that all evidence collapses into a single indistinguishable blur. It survives long enough when produced with sufficient momentum to travel a measurable distance before decaying. That small travel distance is one of the great gifts the lambda gives to experimenters. It is brief, but not too brief. Elusive, but not impossible. The first thing to understand is what a detector actually detects. Particle detectors do not usually function as tiny eyes looking at tiny objects in the ordinary sense. They register interactions. A charged particle moving through certain materials can ionize atoms, produce light, deposit energy, or curve in a magnetic field. Those measurable effects become tracks or signals. Neutral particles are often harder because they do not interact electromagnetically in the same easy-to-follow way. Some neutral particles can still be detected indirectly by the energy they deposit in certain calorimeters or by the charge products they later produce. The lambda belongs to that indirect category. Before it decays, it is neutral, so it typically does not leave the kind of direct charge track that a proton or pion would. Then it decays, and suddenly the story becomes visible. This is why the decay vertex matters so much. A vertex in particle physics is simply a point where something happens, typically where a particle is produced, or where it decays into others. In a high-energy collision, many particles may be produced at a primary vertex, the initial interaction point. If one of those particles is a lambda, the lambda may travel a short distance away before decaying into charged daughters. Those daughters, often a proton and a negatively charged pion, begin leaving visible tracks in the detector from a secondary vertex displaced from the primary one. That displacement is one of the classic signatures of a short-lived neutral particle. The parent is unseen before the decay, but the daughters announce that something neutral must have travelled from the first point to the second. That may sound straightforward in principle, but in practice it requires detectors of remarkable precision. Scientists need to know where the original collision happened, where the daughter tracks seem to begin, how those tracks curve in a magnetic field, and what energies and momenta they carry. Modern detectors are built in layers precisely for this reason. Close to the collision point, there are tracking devices with very fine spatial resolution, capable of measuring tiny displacements. Farther out, there may be additional tracking chambers, calorimeters that measure deposited energy, and systems for identifying particle types. Together, these layers allow physicists to reconstruct entire events from the pattern of registered signals. Take the charged daughters of a lambda decay. Once the proton and pion emerge, they move through the detector material and interact electromagnetically. Because they are charged, their paths can be bent by a magnetic field. The amount of curvature depends on the particle's momentum and charge. A more energetic particle bends less. The direction of curvature tells you the sign of the charge. By tracking that curved path carefully, physicists can infer the momentum of each daughter. This is already a major step, because once you know the momenta of the decay products and can identify their particle types, you can begin reconstructing the parent. Particle identification is its own little art. A proton and a pion are not the same mass, so even if they had similar momentum, they would not behave identically in all parts of the detector. They may deposit energy differently, move with different speeds, or produce different timing signatures. Detectors use several methods to distinguish among particle species. Some systems rely on how much ionization a charged particle causes as it passes through a medium. Others rely on timing, measuring how long a particle takes to travel a known distance. Still others use the light produced when a particle moves through a material at a speed exceeding the phase velocity of light in that medium, which gives additional information about velocity. By combining momentum from tracking with velocity or energy loss information, physicists can decide whether a given track is more likely a proton, a pion, a kaon, or something else. This matters enormously for Lambda reconstruction, because the identity of the daughters is part of the clue. If two tracks emerge from a displaced vertex and one behaves like a proton, while the other behaves like a negatively charged pion, then that pair becomes a strong Lambda candidate. If the momenta and geometry also fit the expected decay pattern, then the case grows stronger still. One does not prove the parent from any single piece of evidence alone. One builds a layered argument from consistent measurements. Particle physics is full of these layered arguments, and they are often more convincing precisely because many independent pieces all point to the same conclusion. Once the daughter tracks are measured and identified, physicists can work backward to reconstruct the invariant mass of the parent particle. Invariant mass is one of the most powerful tools in the field. It is a quantity calculated from the energies and momenta of the final particles that tells you what mass the original parent must have had if those daughters came from a single decay. If many such proton and pion pairs from displaced vertices consistently reconstruct to the same parent mass, and that mass matches the known lambda mass, then one has strong evidence that those events came from lambda decays. This is one of the ways a particle that is never directly seen in its full neutral parent form becomes firmly established as a real and measurable object. There is something almost satisfying about how forensic this is. The lambda leaves no ordinary calling card. It simply departs and lets its daughters handle the paperwork. Yet from those daughters, scientists recover the parent's mass, its lifetime scale, its production rate, and much more. It is like reconstructing an entire conversation from two footprints and a bent teacup, except with better mathematics and less accusation. The lifetime itself can be measured in this indirect way too. Because the lambda travels some distance before decaying, and because its momentum can be inferred from the daughters, physicists can estimate how long it lived before the decay occurred. They do this over very large numbers of events. No single lambda tells the whole story. But if one measures the distribution of decay lengths for many lambdas, taking into account their momenta, a characteristic lifetime emerges. This is another example of the way short-lived particles become experimentally accessible, not despite their brevity, but through the patterned consequences of that brevity. The finite lifetime creates a displaced decay. The displaced decay can be measured. The measurement leads back to the lifetime. Modern collider experiments perform this sort of reconstruction on enormous numbers of events. In a proton-proton collider, for example, high-energy collisions can produce showers of hadrons. Among them may be lambdas, antlambdas, kaons, pions, protons, and all sorts of other short-lived or long-lived particles. The detector records vast amounts of information for each event. Software then searches for combinations of tracks consistent with known decays. A lambda candidate might be built from one positive track that looks proton-like and one negative track that looks pion-like, both originating from a common displaced vertex and yielding the correct reconstructed mass. When such candidates accumulate in large numbers, a mass peak appears above the background. That peak is one of the classic signatures that a real particle species is being observed. Background, incidentally, is the practical problem lurking behind all this. In a busy collision environment, not every pair of tracks that looks vaguely plausible actually comes from a lambda. Random combinations of unrelated tracks can mimic the signature to some extent. Other particles can decay in ways that look similar. noise and imperfect measurements can complicate the picture, so physicists do not merely search for single promising events and declare victory. They use careful selection criteria, known as cuts in the traditional language of the field, to suppress background and enrich the sample in genuine lambda decays. They may require the decay vertex to be sufficiently displaced, the proton and pion tracks to satisfy certain quality conditions, the reconstructed parent to point back toward the primary vertex in the right way, and the invariant mass to fall near the known lambda value. That pointing requirement is a nice example of geometric reasoning. If the lambda travelled from the primary collision point to the secondary decay point, then the momentum of the reconstructed lambda candidate should line up with the direction between those 2 points. If the tracks and geometry imply a parent momentum pointing somewhere completely different, the candidate is less believable. This sort of consistency check is extremely powerful. A real lambda decay has a lawful geometry. Random track combinations often do not. There is also the matter of antlambdas, the antiparticle partners of lambdas. They decay into the corresponding antiparticles, such as an antiproton and a positively charged pion. Detectors can reconstruct these as well. Studying both lambdas and antlambdas allows physicists to compare matter and antimatter, production, test symmetries, and improve understanding of hadronization. The process by which quarks and gluons produced in energetic collisions become observable hadrons, so the techniques developed to detect lambdas also open broader windows into the dynamics of the strong interaction and the behavior of matter under extreme conditions. If we step back in time, the same basic logic was already present in earlier generations of detectors, though the technology was less automated and often much more visual. In bubble chambers and cloud chambers, the charged daughters of lambda decay could literally be seen as tracks in photographs. Experimentalists would examine images, identify V-shaped topologies where no incoming charged parent track was visible, and infer the existence of neutral, short-lived parents. The lambda became one of the classic examples of this style of detection. In modern experiments, cameras have given way to layered electronic detectors and elaborate data acquisition systems, but the conceptual method remains essentially the same. One sees the daughters, reconstructs the parent, and uses repeated events to establish the particle's properties. There is something almost beautiful in that continuity. Technology changes enormously, but the underlying logic does not. The lambda is still found by the trail it leaves after it has ceased to be itself. A neutral parent travels invisibly, decays into charged products, and those products provide the evidence. The whole method depends on the fact that physics is lawful enough for reconstruction to work. If decays were arbitrary, if tracks were not governed by magnetic fields and conservation laws, if particle properties varied whimsically from event to event, then none of this would be possible. The success of detection is itself a quiet demonstration of the orderliness of the subatomic world. One should also mention the role of statistical analysis, because modern particle physics is never just a matter of finding a few nice events and feeling satisfied. Scientists need to know how many lambda candidates they have, how many are likely real, how many are expected from background, how detection efficiencies bias the sample, and how uncertainties propagate through the measurement. This is where the field becomes both extremely powerful and occasionally so full of careful caveats that one begins to suspect all physicists were once trained by very nervous accountants. Every measurement comes with uncertainty. Every selection process can distort the sample. Every detector has limitations, so results are corrected, calibrated, cross-checked, and compared with simulation and theory. Simulation is particularly important. Physicists use detailed computer models of particle interactions and detector responses to understand how a true lambda decay should appear in the apparatus. These simulations include the geometry of the detector, the materials involved, the magnetic field, and the behavior of the electronics. By comparing real data with simulated lambda signals and known backgrounds, researchers can tune their reconstruction methods and estimate efficiencies. This allows them to say not just that lambdas were seen, but how many were likely produced in the first place, with what momentum distributions, in which collision environments, and under what conditions. The detector itself, then, is only part of the story. Equally important are the reconstruction algorithms, the particle identification methods, the selection criteria, the simulations, and the statistical analysis. The lambda is short-lived enough that raw signals alone do not simply announce it. It has to be extracted from a dense environment of data through careful reasoning embodied in both software and experiment design. Particle physics is often described as the study of the very small, but in practice it is just as much the study of the very structured. Without structure in the data and discipline in the analysis, the lambda would remain hidden. There is another reason the lambda is experimentally useful, and it has to do with calibration and benchmarking. Because the lambda has a well-known mass and a characteristic decay topology, it can serve as a check on detector performance. If a detector and reconstruction software are working properly, the reconstructed lambda mass peak should appear where it ought to. The measured lifetime should agree with established values within uncertainty. The decay vertex distribution should behave as expected. In that sense, the lambda is not only an object of study but also a tool. Short-lived though it is, it helps experimentalists verify that their instruments and methods are behaving sensibly. This is one of the quiet pleasures of particle physics. The same particle can be both a subject and a reference. One moment you are studying the lambda because you want to understand strange baryons. The next moment you are using lambda decays to test vertex reconstruction performance in a detector. The particle does not mind. It has already decayed and moved on. High-energy nuclear collisions offer another environment where lambda detection becomes especially informative. In collisions involving heavy ions, a hot, dense medium can be created in which quarks and gluons behave collectively before hadrons form. Studying how many lambdas emerge, with what momenta and in what ratios relative to other particles, helps physicists understand the behavior of strongly interacting matter under extreme conditions. In such studies, the ability to reconstruct lambdas reliably is crucial. Once again, the short-lived neutral baryon becomes a messenger from a hidden stage of the event. Even outside the largest collider experiments, the general principle remains the same. To detect something so short-lived, scientists rely on what lasts longer than the parent itself, namely the pattern of tracks, the displaced vertex, the momentum balance, the invariant mass, the statistical distribution of many events. No one expects the lambda to hold still. Instead, the apparatus and the analysis are built around the expectation that it will not. The experiment is designed not to trap the particle, but to reconstruct its passing. That is perhaps the most important lesson in how scientists detect something so short-lived. They do not ask the impossible. They do not demand that the lambda become ordinary, stable, or directly visible in the naive sense. They accept its nature and build methods suited to it. The detector is a machine for turning consequences into knowledge. The lambda decays. The daughters leave tracks. The tracks are measured. The parent is inferred. The inference is repeated thousands or millions of times. From that repetition comes precision, and from that precision comes understanding. So although the lambda particle exists only briefly and usually hides its neutral self before decay, scientists detect it with remarkable confidence by reading the geometry and kinematics of its aftermath. They find the displaced vertex, they identify the proton and pion, they reconstruct the invariant mass, they measure the lifetime statistically, they compare data with theory and simulation. In doing so, they transform a fleeting event into a stable piece of scientific knowledge, and once that becomes possible, the lambda stops being merely a short-lived oddity and starts becoming something much more valuable, a tool for learning what strange baryons, weak decays, and strongly interacting matter can reveal about the universe as a whole. By the time one has followed the lambda particle through its brief life, from its 3-quark identity to its weak decay, and the careful methods scientists use to detect it, it becomes clear that the lambda is not interesting merely because it is one more entry in the particle catalogue. It is interesting because it reveals a surprising amount about how the universe is built. This is often the pattern in physics. A subject that begins looking very small and specialised turns out to sit at the intersection of several much larger truths. The lambda particle does exactly that. It is a strange baryon, yes. It is unstable, yes. But it is also a window into the structure of matter, the behaviour of the strong and weak interactions, the history of the early universe, the physics of extreme cosmic environments, and even the methods by which human beings manage to know anything at all about worlds they cannot directly see. One of the first things the lambda reveals is that ordinary matter is not the whole story of matter. That may sound obvious now, because the modern standard model has trained us to expect a rich subatomic population, but historically it was not obvious at all. For a long time, one could have hoped that the proton, neutron and electron more or less exhausted the important cast of stable or semi-stable constituents relevant to matter. The lambda helps show that nature permits many more arrangements than the everyday world makes use of. The visible world around us is built from a relatively small and stable subset of the possible hadronic combinations. The lambda belongs to a wider hidden population that the universe allows under the right conditions, even if those conditions are not what dominate in your kitchen, garden or local train station. That matters because it reminds us that reality is not limited to what lasts. Stable matter gives us planets, chemistry and living things, but unstable matter gives us information about the deeper rules behind them. The lambda is not part of the furniture of the everyday world, yet its existence helps explain the grammar of that world. It tells us that baryons are not limited to protons and neutrons. It tells us that quark flavour matters in a concrete and testable way. It tells us that the hadronic spectrum is richer than ordinary matter alone suggests, and in doing so, it reveals something essential about the universe. Nature is not built only from the arrangements that happen to persist long enough to make stars and sandwiches. It is built from a broader set of lawful possibilities, of which stable matter is only the most familiar subset. The lambda also reveals the extraordinary success of the quark model. It is one thing to say in the abstract that hadrons are made of quarks. It is another to show that a specific particle's mass, charge, classification, and decay behaviour all make sense once one assigns it the content of one up quark, one down quark, and one strange quark. The lambda is almost a textbook demonstration of how well the quark picture works. Its neutrality follows from the quark charges, its status as a baryon follows from being a 3-quark state, its strangeness follows from containing a strange quark, its instability follows from the fact that the weak interaction can change that strange quark into a lighter flavour. This coherence is not trivial. It is one of the reasons particle physics became such a powerful explanatory science in the 20th century. The lambda is a small but elegant proof that the underlying model is not just a collection of convenient labels. It captures something real about how matter is organised. More than that, the lambda reveals the division of labour among the fundamental interactions. This is one of the most important lessons hidden inside its short life. The strong interaction binds the lambda together as a hadron. Without that, the particle would not exist. The weak interaction causes its decay. Without that, the particle would remain a strange baryon. The lambda therefore embodies, in one compact example, the fact that the universe does not operate through one generic force doing everything at once. Different interactions govern different aspects of reality, each with its own permissions and prohibitions. The strong interaction is immensely powerful, but does not change quark flavour in the way the lambda needs for decay. The weak interaction is far less powerful but has exactly that flavour-changing ability. So the lambda shows that what matters in physics is not only how strong a force is, but what it is allowed to do. That is a very deep lesson, and it extends well beyond this one particle. The universe is not simply a place where the strongest effect always wins in every sense. It is a place where distinct interactions shape different parts of the story, according to specific rules. the lambda makes this visible in a particularly crisp way. It is born through the kind of energetic hadronic processes that the strong interaction dominates, then dies through the weak interaction, because only the weak interaction can alter the strange quark's flavour. In that sense, the lambda is a beautifully compact example of how the standard model partitions the responsibilities of the cosmos. The lambda also reveals the reality of strangeness, not just as a historical label, but as a genuine structural feature of matter. Before quarks were accepted, strangeness entered physics as a way of organising puzzling experimental behaviour. Strange particles were produced rapidly, but decayed more slowly, suggesting hidden bookkeeping rules. The lambda was central to that story. In the modern picture, the mystery becomes clearer. Strangeness corresponds to the presence of a strange quark. The lambda carries that quark in its internal makeup. So when physicists study the lambda, they are not merely revisiting a historical oddity. They are directly probing how flavour works in hadrons. The lambda shows that quark flavour is not a decorative classification. It has measurable consequences for mass, production, and decay. And because of that, the lambda reveals something about symmetry and its limits. Particle physics is filled with symmetries, patterns, conservation laws, and approximate regularities that help organise an otherwise bewildering zoo of states. The lambda fits into symmetry schemes among baryons, yet it also reminds us that these symmetries are not absolute in every simple sense. The strange quark is heavier than the up and down quarks, so the world is not perfectly symmetric among flavours. The weak interaction violates certain symmetries such as parity in ways that show up in the angular distributions of decay products. The lambda therefore teaches a subtle lesson. The universe has order, but not naive order. Its symmetries are real, informative, and deeply useful, yet often broken or limited in ways that are themselves physically revealing. That point becomes especially important when one thinks about parity violation. In weak decays of lambda particles, the weak interaction reveals its strange disregard for perfect mirror symmetry. This was one of the great conceptual shocks of 20th century physics more broadly, and the lambda belongs to that family of phenomena that made it impossible to pretend the laws of nature were indifferent to left and right in all circumstances. By studying the polarization of lambdas and the angular distribution of their decay products, physicists can probe how the weak interaction behaves inside baryons. So the lambda reveals not only that the weak force changes flavour, but that it does so in a way that reflects the deeper asymmetries of the laws themselves. The lambda also reveals the internal complexity of hadrons. It is easy to say a baryon contains 3 quarks, but the reality inside a hadron is much more dynamic than that simple sentence suggests. The quarks abound in a sea of gluonic activity and quantum fluctuations. The mass of the hadron arises not merely from the bare masses of its constituent quarks, but from the energy of the strong interaction and the motion of the constituents inside the bound state. The lambda therefore reveals that even a seemingly modest hadron is not a static little container with 3 neat occupants. It is a highly non-classical, strongly interacting quantum object. This is important because it teaches us not to take the simple pictures too literally. The simplified quark content is true and useful, but the underlying reality is richer and more dynamic. In that sense, the lambda helps reveal one of the most profound facts about the material universe, namely that much of the mass of ordinary matter comes from interaction energy, rather than simply from the intrinsic masses of tiny constituent particles. This is true for protons and neutrons as well, and therefore true for the visible matter of the universe. The lambda, as another baryon bound by the strong interaction, belongs to that same lesson. Matter is not heavy only because its constituents are heavy. Matter is heavy because the strong interaction stores energy in bound states, and that energy appears as mass. The lambda helps reinforce that point. Even strange baryons participate in the same deeper story that makes the material world substantial. There is another, more cosmic way in which lambda particles reveal the universe, and it has to do with extreme environments. Under ordinary earthly conditions, lambdas are not part of stable matter around us. But in high-energy astrophysical settings and in dense nuclear matter, strange baryons may play a more active role. Inside neutron stars, for example, matter is compressed to extraordinary densities, and physicists have long considered the possibility that strange baryons such as lambdas may appear in the interiors of such stars. If that happens, their presence could affect the equation of state of the matter inside, which in turn influences how large or compact neutron stars can be, how they respond to pressure, and how they behave when observed through gravitational waves or electromagnetic signals. That is a rather astonishing reach for such a short-lived particle. A lambda produced in a collider or cosmic interaction on Earth lasts only a tiny fraction of a second, yet the physics associated with lambdas may matter in the long-term structure of some of the densest objects in the universe. This is one of the delights of physics. The local and the cosmic are never quite as separate as one might assume. The same rules governing a strange baryon in a laboratory experiment may also shape the behaviour of matter, packed inside a dead star tens of thousands of light-years away. So the lambda reveals that particle physics is not a sealed little discipline concerned only with abstract miniatures. It is woven directly into astrophysics and cosmology. Heavy ion collisions provide another example. When nuclei are smashed together at extremely high energies, a hot dense medium is created in which quarks and gluons can behave collectively before hadrons form. In these environments, lambdas and other strange hadrons become important probes of how strongly interacting matter behaves under extreme conditions. Their production rates, momentum distributions, and relative abundances compared with non-strange particles tell physicists about the hadronization process, and about how quark-gluon matter turns back into ordinary hadrons as it cools. In this way, the lambda reveals something about the universe not only as it is now, but as it may have been in the very early moments after the Big Bang, when temperatures and densities were so extreme that ordinary hadronic matter had not yet settled into its familiar forms. There is a subtle beauty in that connection. The lambda, though fleeting, carries information about conditions under which the universe itself once operated as a much hotter and stranger place. By learning how lambdas are produced, and how strangeness emerges in energetic environments, physicists gain clues about the dynamics of the early universe. One should be careful not to overstate the directness of this analogy, because modern collider environments are not simply the early universe in miniature, but they do give access to some of the same underlying physics of strongly interacting matter at high temperature and density. So the lambda reveals not only the architecture of matter, but something of cosmic history as well. The lambda also reveals how science works when direct perception fails. This is easy to overlook because particle physics results often get presented as tidy facts once the hard work is done. But the lambda is a particularly good reminder that much of modern knowledge is inferential without being speculative. Scientists do not see the lambda in the way one sees a candle or a cloud. They reconstruct it from displaced decay vertices, daughter particle identification, invariant mass peaks, lifetime distributions, and the repeated consistency of those signatures across many events and many experiments. The lambda therefore reveals the epistemology of modern physics, if one may use that slightly grand term without sounding too pleased with oneself. It shows that direct visibility is not the same as knowability. A thing may be hidden, brief, and neutral, yet still become an object of precise knowledge through lawful consequences. That, in turn, reveals something about the reliability of the universe itself. The reason inference works so well is that the laws of physics are stable and structured. A lambda decay today follows the same rules as a lambda decay yesterday or in another laboratory. Conservation laws hold. Magnetic fields bend tracks predictably. Mass reconstruction gives the same answer again and again. If reality were whimsical at the small scale, there would be no such thing as particle physics in the modern sense, only a collection of unreliable anecdotes. the lambda reveals that even fleeting things are orderly. It is one more instance of the universe proving far more intelligible than it strictly had to be. It also reveals how much meaning can be packed into instability. In ordinary language, instability sounds like a defect. In physics, instability is often an opportunity. The lambda's weak decay teaches us about flavor change. Its lifetime teaches us about interaction strengths. Its decay asymmetries teach us about parity violation. Its production in collisions teaches us about hadronization and the dynamics of strange quarks. Its possible role in dense matter teaches us about astrophysical extremes. In other words, the lambda reveals that temporary states are not second-class citizens of reality. They are often among the most informative. Stability builds the world we live in. Instability helps explain it. This brings us to another important point. The lambda reveals that the standard model, for all its limitations, is a remarkably successful framework. The model tells us how quarks are organized, how they interact via gluons, how flavor can change through the weak interaction, and why particles like the lambda should exist and decay as they do. That does not mean the standard model is final or complete. It does not explain everything. It leaves unanswered questions about dark matter, neutrino masses in their deepest sense, the origin of the quark mass pattern, and much else. But when it comes to the lambda, the standard model performs with admirable precision. The particle's existence, classification, and decay are not mysterious once the framework is in place. That is worth appreciating. The lambda reveals not only truths about the universe but also the genuine explanatory power of the theories humans have built. At the same time, it reveals where the edges of explanation still lie. Why 6 quark flavors and not some other number? Why the strange quark has the mass it does? Why the pattern of weak mixing among quarks has the structure observed? Why the standard model parameters take the values they do? The lambda does not answer these questions by itself, but it points toward them. It shows the consequences of those deeper facts in one concrete case. In that sense, the lambda is both a solved object and a reminder of what remains unsolved. Good particles often do that. They cooperate just enough to teach us something and withhold just enough to keep the field employed. There is also a broader human lesson in the lambda's story. The universe often reveals its deepest structure not through the biggest and most obvious objects, but through brief, indirect, and initially puzzling phenomena. The lambda was not discovered because someone set out to admire its elegance from the beginning. It emerged from odd tracks, strange lifetimes, and awkward classification problems. Only later did its full significance come into focus. This is true of much of science. Clarity arrives through persistence with the initially inconvenient. The lambda reveals that nature's most useful clues may first appear as anomalies, as things that do not fit the current picture and therefore force the picture to improve. And perhaps that is the most satisfying thing it reveals of all. The universe is not simple in the way one might wish after a long day. It is layered, rule-bound, generous in possibilities, and occasionally determined to hide its workings behind particles that live for only the briefest of moments. Yet despite all that, it can be understood. The lambda particle, with its strange quark, its weak decay, its displaced vertex, and its place in the hadron family, becomes a tiny but vivid proof that the deep world is accessible to thought and experiment. We may never watch a lambda the way we watch the moon rise or steam curl from tea, but we can know it, measure it, classify it, and use it to reason outward towards stars, cosmic fireballs, and the very structure of matter. So what does the lambda particle reveal about the universe? It reveals that matter has hidden depth. It reveals that quark flavor is real and consequential. It reveals that the strong and weak interactions divide the labor of nature in precise ways. It reveals that unstable particles are often among the most informative. It reveals that the laws of physics are orderly enough for indirect knowledge to become exact. It reveals that strange hadrons may matter in environments as extreme as heavy ion collisions and neutron stars, and it reveals that even something fleeting and neutral can illuminate the architecture of reality far beyond its own tiny lifespan. By now, after all this quiet time spent with a particle that barely lingers, the broad picture begins to settle. The Lambda started as a name, then a strange baryon, then a weakly decaying clue to deeper laws, and now it has become something more reflective than that, a reminder that the universe often says its most important things very quickly. Which feels like a good place to begin easing back out of the particle world, not with a hard stop, but with the gentler task of looking once more at what this short-lived little resident of the quantum zoo has really left behind in the mind after it is gone. And so, after all that time spent with a particle that hardly seems willing to stay in one place long enough to be introduced properly, we find ourselves easing back from the Lambda and the crowded little world it belongs to. Not leaving it behind exactly, because once you have looked into matter at that depth, it never quite returns to being simple again, but stepping back enough to notice what kind of journey it really was. We began with a name that sounds almost modest, the Lambda particle. Nothing too alarming in it at first glance. It could almost pass for something orderly and discreet, the sort of term one might meet in a textbook and assume would remain politely in its lane. Instead, it turned out to be a doorway into a much larger landscape, one in which matter is layered, identity is built from quarks and forces rather than surfaces and shapes, and instability is not a flaw but a clue. What strikes me most, on the way back out, is how often physics asks us to revise the meaning of ordinary words. Particle, for one. In everyday thought, a particle sounds like a speck, a tiny grain of stuff, something hard and simple and comfortably small. But the Lambda taught us otherwise. It is not a grain. It is a bound state, a quantum arrangement, a 3-quark baryon held together by the strong interaction, and defined by a whole set of properties that make sense only once we stop imagining little marbles and start thinking in terms of deeper rules. It is made of 1 up quark, 1 down quark, and 1 strange quark. That much is already clear. But what that means, really, is that the Lambda exists because the universe allows a particular combination of flavour, colour neutrality, spin, and binding to come together briefly as one lawful state. Then there is unstable, another word that does not survive the trip unchanged. At first hearing, unstable sounds like something precarious, something badly made, something likely to collapse because its structure is weak. But the Lambda is not weakly made at all. It is strongly bound. That is one of the most important things about it. The strong interaction holds it together as surely as it holds together any baryon. What makes it unstable is not poor construction, but the existence of another allowed future. Its strange quark can be transformed by the weak interaction into a lighter quark. Once that happens, the particle can no longer remain what it was. So the Lambda is unstable in a precise and dignified sense. It is a valid state, just not a final one. There is something rather profound in that if one lets it sit for a moment. Reality, at least at the subatomic level, is full of things that are completely real without being permanent. That seems worth remembering beyond particle physics as well. We tend to trust what lasts. Mountains, old cities, stars that outlive civilizations. Duration feels like evidence of seriousness. The Lambda disagrees. It lasts only briefly. Yet from that short life, physicists can learn about the structure of hadrons, the division of labour between the strong and weak interactions, the meaning of strangeness, the behaviour of flavour-changing processes, and even the conditions inside dense astrophysical objects. It is a tiny, temporary thing with a very large informational footprint. If that is not a respectable way to exist, I am not sure what is. Another thing that lingers, as one drifts back through the particle world, is how layered matter really is. The ordinary human relationship with matter is reassuringly straightforward. Things are solid, tables are tables, air is air. A cup remains where you put it, unless of course you place it near the edge of a desk while looking for your phone, in which case the laws of gravity become extremely educational. At our scale, matter appears stable and continuous. The atom itself once seemed like a final answer, the smallest indivisible unit. Then the atom opened into electrons and nuclei. The nucleus opened into protons and neutrons. Protons and neutrons opened into quarks and gluons. And even there, the story did not become simple. Instead, it became dynamic. The proton was not just three quarks parked neatly together. The lambda certainly was not. These were active, strongly interacting systems, rich with motion and energy, their identities emerging from quantum fields and conservation laws, rather than from any tiny mechanical arrangement visible to common sense. That hidden richness is perhaps one of the most comforting and unsettling things about modern physics. Comforting because the world is far more structured than it first appears, unsettling because the structure is so unlike the picture our instincts would draw for us. We like final layers. We like a last brick in the wall. The lambda belongs to a universe that is less brick-like and more relational than that. It exists because of interactions. Its properties matter because of symmetries and conservation laws. Its mass is not merely a sum of ingredient labels. Its decay is not an accident, but a consequence of the weak interaction's permission to change flavour. Even its discovery came not from direct sight, but from tracks, displaced vertices, reconstructed masses, and statistical patterns. The lambda is not the sort of thing one ever really sees in the ordinary sense. It is the sort of thing one learns to know by the shape of the consequences it leaves behind. That too feels like a larger lesson. So much of science is not direct viewing, but disciplined inference. We often speak as though seeing is the gold standard and everything else is somehow second best. Yet the lambda particle makes a mockery of that hierarchy. No one watches a lambda in the way one watches rain on a window, and still physicists know it with extraordinary precision. They know its mass, its lifetime, its common decay modes, its role in the hadron spectrum, its production behaviour, and the physics its decays reveal. They know it because the universe is lawful enough that indirect evidence can become exact knowledge. That is one of the quiet triumphs of modern science. The hidden does not have to remain unknowable. It only has to leave a reliable trail. I find there is something rather gentle in that idea. The lambda itself never lingers. It is gone almost immediately by human standards. Yet what it leaves behind is enough. Two charged tracks, a secondary vertex, a reconstructed invariant mass, a statistical lifetime. From those traces a whole picture emerges, and perhaps this is why particle physics, for all its technical difficulty, can sometimes feel almost philosophical without trying too hard. It keeps showing us that reality is not obliged to be directly visible in order to be deeply real. It keeps reminding us that what matters may first appear as an aftermath. The lambda also leaves behind a historical lesson that is easy to appreciate on a second look. When strange particles first appeared, they seemed awkward. Their behaviour did not fit comfortably into existing expectations. They were produced quickly, decayed more slowly, and generally behaved like guests who had not read the seating plan. The response of physics was not to declare the universe unreasonable and give up. It was to look for a deeper organising principle. Strangeness was introduced. Later the quark model clarified it. The strange quark gave the category a concrete basis. What began as a problem became a doorway. That pattern repeats across science often enough to be one of its defining rhythms. An anomaly appears. It causes trouble. Trouble forces better structure. Better structure reveals a deeper truth. The lambda was one of those constructive inconveniences, and physics is much richer because it refused to ignore it. There is also the sheer elegance of the lambda as a teaching object. It sits close enough to ordinary baryons to be understandable, and far enough from them to be revelatory. A proton and neutron are familiar once one has spent any time in particle physics. They are the sturdy household names of the baryon family. The lambda is their quieter, stranger relative. Same broad family, same 3-quark logic, same strong interaction holding things together. And yet add one strange quark, and the whole character changes. The mass rises. The decay channels change. The lifetime changes. The historical role changes. Suddenly the baryon becomes not part of everyday stable matter, but part of the richer hidden hadron world. Few examples show so clearly how one deep ingredient can alter an entire physical story, and in the background of all this lies the larger quiet astonishment that the standard model, incomplete though it surely is, describes this world so well. The lambda fits into it beautifully. The quark content makes sense. The classification makes sense. The decay through the weak interaction makes sense. The strong interaction binds it as expected. The experimental signatures appear where they should. There are still unanswered questions, many of them large and important. Why this pattern of quark masses? Why 6 flavors? What lies beyond the standard model? How dark matter fits into the wider story? But the lambda remains one of the many examples where the existing framework works with almost unnerving precision. It is worth pausing over that now and then. Human beings, small creatures on a rocky planet, have somehow managed to infer the behaviour of particles that last for only tiny fractions of a second and are known chiefly through invisible constituents and indirect traces. That is not a bad day's work for the species. The lambda also helps soften a false divide between the small and the vast. It is easy to think of particle physics as the study of tiny things in sealed laboratory worlds, while astronomy and cosmology deal with the grand sweep of the universe. But the lambda refuses to stay in its lane there as well. Strange baryons may matter in neutron stars. Their production matters in heavy ion collisions that help us understand strongly interacting matter under extreme conditions. The same physics that governs the lambda's brief existence in a detector is tied to the deeper behaviour of matter at densities and temperatures far beyond everyday life. The small is not separate from the cosmic. It is one of the ways the cosmic becomes intelligible. That connection, I think, is one of the loveliest parts of the entire topic. The lambda is tiny, fleeting and hidden, yet it reaches outward conceptually towards some of the largest questions we can ask. What is matter made of? How do the forces differ in their roles? How does the universe behave under extreme conditions? What sorts of particles can exist even if briefly? How do we know what we cannot directly see? These are not small questions at all. The lambda simply gives them a very compact and efficient stage on which to play out. Now, after all this, we might ask whether the lambda particle itself cares about any of this. Almost certainly not. One does have to guard against projecting too much personality onto the residents of the quantum world. The lambda does not take pride in its strange quark. It does not consider its lifetime scientifically useful. It does not feel honoured to have contributed to the history of particle physics. It is a lawful state of matter, nothing more and nothing less. And perhaps that is part of the beauty. The universe does not perform for us. It simply is what it is. The lambda is one brief expression of that deeper order, and we are the ones who add narrative, curiosity, and the slightly overexcited delight of having understood even a little of it. If you have stayed with me this far, then somewhere along the way we have done something rather nice together. We took a particle that most people will never hear mentioned outside a physics context, and treated it not as a footnote, but as a proper subject of attention. We gave it time. Which is slightly ironic, of course, because the lambda itself gets so little of it. But perhaps that is exactly why the exercise feels worthwhile. The universe is full of phenomena that pass too quickly for ordinary life to notice, yet they are still part of the great machinery underneath everything. Spending a little while with one of them is a way of enlarging the world without moving an inch. So now, as we drift back out of the particle world, the larger surface of reality starts to return. The room around you, the chair or bed beneath you, the late hour perhaps, if it is late where you are, the ordinary quiet of objects that seem stable and complete in themselves, and yet they are not simple anymore, not quite. The walls, the air, your hands, all are built on layers of structure deeper than they first appear. Somewhere far below the human scale lies the same strong interaction that binds quarks into baryons. Somewhere in the hidden logic of matter lies the possibility of strange quarks and lambdas and weak decays and all the subtle bookkeeping that keeps the universe consistent. The everyday world has not changed while you listened, but perhaps its depth has become a little easier to feel. I suppose that is one of the real pleasures of physics when approached gently enough. It does not have to tear the world apart in order to enrich it. It simply adds dimension. A table remains a table, but it also becomes a triumph of stable baryonic matter, electromagnetic structure, and quantum rules that have somehow cooperated long enough to support your cup without complaint. A night sky remains a night sky, but it also becomes a place where extreme matter, dense stars, high-energy events, and particle processes beyond everyday experience continue their quiet work. The lambda particle becomes one thread among many in that larger fabric, brief in itself, but connected to almost everything. And now, before we leave it there, let me ask you once more, gently, where are you listening from tonight? And what sort of hour is it in your part of the world right now? It feels fitting to return to that kind of question after spending so long with particles whose own lifetimes are far too short for clocks we would recognise. Perhaps it is late enough that the room has gone still and the day has finally loosened its grip. Perhaps you are listening in the soft aftermath of evening, when thoughts begin to blur at the edges and the mind is content to follow one last trail of curiosity before sleep. If this quiet journey through the lambda particle and its brief little life has given you some calm, some interest, or simply a pleasant place to rest your thoughts for a while, I would be very grateful if you liked the video and perhaps subscribed as well. It helps this corner of slow science find others who may want the same sort of company. And if the subject kept you awake a little longer than intended, well, at least you have spent the time in the company of quarks, strange baryons, and one of the more revealing short-lived citizens of the universe. For now, though, we can let the particle world recede a little. The lambda has done its work. It appeared. It told us what it could. It became something else. And what remains is not the particle itself, but the shape of understanding it left behind, which may be the most human kind of permanence we ever get. So wherever you are, and whatever time it may be there, I hope the rest of your night is a gentle one.